So, Assalamu alaikum, ya shabab. I want to welcome who joined. Dr. Antar was with us now, and he is still there. Mr. Abdul Rahman, Mr. Muhammad Mutlaq, Mr. Naif, Salama, Abdullah. So we have 5 joined, other than Dr. Antar and myself. Dr. Antar, how many in the class, 24 or 25?
They are 22 يا دكتور إسماعيل.
22. Okay.
من الريكوردز اللي عندي وأكد لك يعني.
تالي كنت مرة شفتهم في البلاك بورد.
No, they are 22 يا دكتور.
So still we have 5 minutes.
Yes, still they will join. Yes, in the next. يعني عندي لسه at 12:41, so they will join eventually يعني.
طب sorry for disturbance يا دكتور.
لا أبدا فيش أبدا فيش disturbance ولا حاجة. Yeah, I'm admitting some who joined are joining now.
السلام عليكم.
عليكم السلام ورحمة الله وبركاته.
أهلا دكتور.
أهلا.
We are asking the guys in the WhatsApp group to join in now.
Yeah, it's okay. We have 4 minutes to go. Actually, I prepared the lecture for today. I think it's involved, like module 1 also is heavily involved. So we need to manage the time as efficient as possible. That's why I need to start on time.
Excuse me, Dr. Muhammad?
Yes.
Dr. Antar is with us now?
Yes, he is.
Dr. Antar, assalamu alaikum.
عليكم السلام ورحمة الله وبركاته.
Before we start today's module, I really want to ask you regarding the test next week, inshallah, on Saturday.
نعم.
If you can just send us maybe email regarding the specification of the test, for example, the length of the test and how it will be gonna be conducted through Blackboard or something. Yeah.
طيب, okay. Actually, I got a message from Dr. Mohini that we are going to make like a meeting, maybe tomorrow or on Monday, so that we make sure that the way the tests are conducted are somehow streamlined over the courses. So once we finish it, I will give you detailed information in an email.
Okay, خلاص. شكرا.
السلام عليكم.
السلام ورحمة الله وبركاته.
مساء الخير دكتور اسماعيل.
وعليكم السلام، الله يخليك. I think I will start now, even if you are to join. maybe 7 or 8 more to join us. First, I would like to welcome all of you and make sure that you are seeing my screen.
Yes, we do.
Yes.
This lecture, I put a PDF for it, and as I was telling Dr. Hunter, that it will need minor tuning and editing. Like, for example, in the first slide, I put my contact, my information, but I forgot to put my email, so I added this morning. And you have my contact, so I will not go through introducing myself more, because Dr. Hunter did that in the first session, I think. I wanted just to quickly share my thoughts, and also that is related on how we are going to do in general in your master program about engineering. There is a say in Britain that the engineer is a greedy and lazy person. So why greedy? Because he need to maximize what he gain with respect to what he pay. And in our words, what is this? What we call this gain over input, or what we gain over what we pay, we call it efficiency. So engineer always try to maximize the efficiency, isn't it?
Yes.
And this is all we want, that we need to have efficient process, efficient system. Also lazy, because the engineer used to develop equipment and devices to do our work. Like we invented the cars, the trains, the aeroplanes, the elevators, the motors, the engines, right? All this to do some jobs, either in the workshop or even, and instead of walking, then we are using the cars. So what is the role of engineer in general? In general, we learn some science and convert it into technology. This science can be physics, it can be chemistry, math, or mechanical engineering or electric engineering. So is the engineer, or our engineer who will graduate from our master program, will do what? Will develop only technology or efficient and economic technology? So engineer knows the science, converted into efficient and economic technology. And I think Dr. Antar introduced and focus on efficiency and economics in the first module. Today we are going to talk about gas power cycles. Of course, last session or module, Dr. Antar talked about steam cycles, because the course is energy conversion. We convert energy from one form to another form. The form we have in this power plant is the chemical energy in the fuel. We burn it, convert it to thermal, and then into mechanical or electric energy. The power generation in generally worldwide is from different resources, like crude oil is a majority, 36%. Coal maybe in US and Russia or China as well. Natural gas also in our Middle East, it's abundant, and other sources may be renewable energy like solar, wind, tide energy, and other forms. The challenges that facing the world at the moment is the increasing demand due to increase in population. And this is always the case in all countries, especially young countries like in the Middle East. Our population is young, or young men who will create families and have more population. Also in countries like our countries, we are building new cities, new industry. We have industrial city 2 in Jubail, in Gazan, we have Neom now. All these need power generation to support the development. Also declining the economically, the recoverable supplies like oil, natural gas, they are depleted. It is not renewable. They are being consumed, and consumed now with higher rate than before. Also the global climate change, that the temperature of the earth or the globe is going higher than normal, due to the accumulation of greenhouse gases like CO2 and the other gases that accumulate in the outer space of the Earth, representing a blanket that allow sun radiation come in the morning and doesn't lose it by radiation at night. Normally, sun radiation come in the morning, the Earth lose it at night to the dark sky, so the temperature is balanced. But because these greenhouse gases, CO2 and some refrigerants, they cover the outer space, so they allow the sun radiation to come in the morning, but they don't allow it to go out at night in the dark side of the Earth. So this accumulate heat over time, and the temperature of the globe increase, creating a lot of challenges that you know it very well. If you can think about other challenges for the sector of power generation, you can list or add to us through chat or through any discussion. In US, the resources of energy, mainly coal, as you can see, 48.5%, which it's a problem. In combustion, it has a lot of pollution. Natural gas, you have 21%. We have also a good portion from natural gas. Nuclear is 19. We are starting here in our area, starting hydraulic and other renewable is within maybe 8 to 10%. Of course, we have here in Saudi Arabia, if you want to know what is the main source of energy we are relying on now, simply oil and gas. But the kingdom is now, according to 2030 vision, we are going to increase the renewable. We hope to reach maybe 20% by 2030, but that's why KKR is taking, and also KKR is taking care of nuclear. Here's this link is actually giving idea about the sources of energy in Saudi Arabia. If you are interested, you can open this link. Again, related the energy, possible energy conversion of different sources for coal, because coal combustion always produce soot and is very dirty. I mean, from combustion point of view, that's why we don't need to have it with gas turbine, but we have it with boiler, which is mainly Rankine cycle. Natural gas is a clean fuel, so we can use it, burn it, and introduce directly the exhaust gas to brighten. But can we use coal for natural gas? Yes, but we have a process first called gasification. We can convert the coal into gaseous fuel, then take this gaseous fuel, burn it as natural gas. They call it syngas sometimes, or synthesized gas, and they burn it with normal, like natural gas. Of course, we have nuclear fuel. The nuclear fuel usually with the Rankine, but also there are some types of nuclear reactors that can be cooled by gas, not by heavy liquids. So we can cool it by gas, so it will be close to Brighton cycle, but they are not very popular. Oil fuel suitable for Rankine, but maybe some time of fuel. What do you want, Rakan?
Yeah, I just have a quick question, Doctor.
Please.
To link the previous lectures with this lecture, what is the main difference between the Rankine and Brighton cycles?
Yeah. Thank you for the question. Rankine, usually we have liquid, like mainly water. We convert it into steam. That's why we store the energy from the fuel in the combustion. We take it to store it in the water by converting it into steam. Then we take this steam that is at high pressure, high temperature to rotate what we call a steam turbine, that is designed to be run by steam. In the Brighton cycle, we have gases. We don't have liquid. Okay, we have all the way gas throughout the cycle. Like that's why we call it gas turbine cycle. But the main concept is the same. You do have a heat addition process. You do have expansion in a turbine. You have a cooling, imaginary, even gas turbine here, imaginary cooling. We are going to discuss these details soon. And we then have the raising pressure device. For Rankine cycle, because we raise the pressure while the fluid is liquid, we use pump. For gas turbine, we raise the pressure. We take the air directly from the surrounding and we raise its pressure by compressor. But we have two heat addition process, two heat addition and heat rejection, two heat transfer process, one heat addition, one heat rejection, and two expansion and compression process. The basic process of the two cycle is the same, but the difference is in the working fluid. Okay?
Yeah, so every Rankine cycle can have a Brayton cycle with it, but not vice versa, right?
Can you clarify the question again, please?
Yeah, I'm asking, like Rankine, you can have the liquid and steam, doesn't matter, but in Brayton it's only gas. So within the Rankine cycle, I can have a Brayton cycle?
No, actually we cannot say this. Actually, Brayton and Rankine are two different engineers. Each one invented the cycle, tried to imitate or Carnot cycle. Carnot is a French scientist who said that if we have a cycle consist of two isothermal, two isentropic process with no friction, nothing, it would be the most efficient cycle. And he calculated on theory what is its efficiency and said this is the ceiling of efficiency of any thermal cycle that convert heat into work, right? According to the second law, which Dr. Antar revised last module. After Carnot came the engineer want to make this theoretical cycle into ground. You need to convert this theory, how to make isothermal heat addition. They find that if we have liquid that is in phase change, like the water when it boils, it can convert, you can add heat to the water while its a temperature constant. This Rankine based his idea on this, that I can have heat addition at constant temperature, which I convert liquid into vapor. Then I can take this vapor at high pressure, high temperature, expand in a turbine. Then I have heat rejection at constant temperature, which is the condensation. When we condense the vapor into liquid bag by cooling it, I can absorb this heat or reject the heat out of my cycle at constant temperature. Then I raise the pressure again while it is liquid by a pump. This is actually Rankine saw this way. Then when he started to build his cycle, he found that he cannot always have the heat addition from liquid, saturated liquid to saturated vapor, because all the work will be in the wet region and the turbine blade will be eroded. So he has to make superheating. So what he did at the end, he has the heating process at constant pressure rather than part of it, major part of it is at constant temperature like Carnot, but beginning of the heating the water from, let us say, 40 degree or 20 degree up to saturated point at high pressure, then constant temperature while phase change, and then superheating. So mainly it is constant pressure, but it has some part at constant T as well. But that's why it is deviated from Carnot. For Brayton, he tried to keep the two isentropic, which is the compression and expansion, two isentropic like Carnot, but the heat addition, he couldn't do it isothermal because he's using gases. At the beginning, Rankine and Brayton think to use a common fluid that are cheap. As you know, the word fluid work for liquid and gases. Water is very available and cheap, so use the water for Rankine or steam cycle. And for air is very abundant and has no price, so they use it in gas cycle or Brayton cycle. Now that's why we cannot say within Rankine cycle there is a Brayton. No, there is a process similar, but not the cycle is named after who invented the cycle, like the gas cycle invented by Brayton, so we call it like this. Steam cycle invented by Rankine, and it is known that we are using liquid that we convert to vapor. The processes are similar, but the fluid is different. Okay.
Clear.
But
Thank you very
we
much.
might add the two cycles together and make link between, as we'll see here, and we call combined cycle. We have the two cycle help each other, right? As we'll see by the end of this module. But we'll call it combined cycles that have two cycles, Brighton and the steam, or gas cycle and the steam cycle. By the way, in Rankine cycle, when we change the fluid from water to any other liquid that convert into vapor at a relatively acceptable temperature, we call it organic cycle because we use organic fluids like CO2, propane, we use ammonia, we use other liquids or substance. We don't call it Rankine, we call it organic. It is there now because sometimes we have a source of low temperature like solar heating or geothermal heating that the temperature cannot go to 300, 400 degree or 500 degree to heat the fluid. So we use other fluids and we don't call it Rankine because Rankine is linked to water. But the same process, I can use ammonia. I can use any other liquid substance that can convert onto vapor and is still based on Rankine cycle. That's we call it organic Rankine cycles. You call it ORC, organic Rankine cycle. Just to say that the fluid is not water. But Rankine cycle alone, it is known that the fluid is water. And you remember, in Rankine cycle, we have two isentropic process, compression in the pump, expansion in the turbine, and two isothermal heat transfer, heat addition in the boiler, constant pressure also, constant pressure, heat addition in the boiler and heat rejection in the condenser. So two isentropic, two isobaric. In Brighton, the same, two isentropic and two isobaric, but the fluid is gas. Okay. So this is just to link what is the proper cycle to convert the energy or thermal energy into electric or mechanical energy, depend on the source of the energy, what is the suitable cycle. In the table, we show that mainly Rankine and gas turbine cycle are the common cycles. Last module with Dr. Hunter, you reviewed and updated yourself about Rankine cycle. Here we are going to talk about gas cycle, and we are going to talk about Brighton cycle, invented by Brighton. For gas power system, we need to review power cycle in general as a concept. Also, when we have the process diagram is a diagram that give us or draws a relation between two properties, like for example, pressure and volume, or temperature and entropy, or enthalpy and entropy. Two processes, how they vary together with respect to each other during the process. This is we call process diagram. So usually common, we use PV diagram and TS diagram. What does that mean, the area under the curve in each diagram? We quickly go through it. And the ideal gas relation, since we are going to talk about gases. So for simplicity, we need to treat gases as ideal gases. Like especially we have air in the cycle, right? And in the gas turbine, we use air. So ideal gas model will be quickly revised. This is a concept of thermal cycle, like your car engine, gas turbine, steam turbine cycles. You have a source of heat at high temperature. Usually you take it to the fluid in your cycle. In this box, as there is a cycle, either it is a steam or gas cycle. You heat your fluid and then you make it rotate turbine, gas turbine, or a steam turbine, or even rotate your car engine and take work. This work out is a net work actually, because we have work in to raise the pressure in pump for Rankine and compressor in gas turbine. The net work, which is the difference between work turbine and work pump or work compressor, is the network of the cycle. But to complete your cycle, like in the steam cycle, you need to convert the gases out of or the vapor out of the turbine into liquid. Why into liquid? To reduce a specific volume and use a small pump to reduce the pressure. This is the science part in it, that we know from thermodynamic tables that gases usually have large specific volume or a small density. Liquids has a small specific volume. So according to the shaft work integration of VDP, or shaft work for pump or compressor integration of VDP. So when we pay work, we need to have a small specific volume. That's why we need to condensate the steam to be liquid, to have a small specific volume. For gases, we need to cool it to have the specific volume. So that's why we need to reject the heat to cool, either to condensate the steam into liquid or to cool the gas. Again, if we have a closed gas turbine, but usually we need to have fresh air. I'll talk about this point again, but the energy balance from first law, net work equal for a cycle, the net work equals the net heat transfer. What is the mean of net heat transfer? Is Q in minus Q out, or Q added minus Q rejected. And the efficiency of the cycle, as we know, what we get is the net work over what we added here is the heat, because the heat is what is the combustion energy, or the energy released by combustion by burning the fuel. This fuel has a price. Imagine you burn 1 barrel of oil, okay? You convert it into electricity through one of these cycles, or you export it with $50, or few years back it was $120, which is better to you. So this is money. Or you convert it into plastics and you have its price higher and higher. So this Q is actually money, right? So what we gain, electricity also is money, because the electric company sell the electricity. And also you use electricity to do some valuable things to you. So work, electric work here is money. The fuel you burn is money. So this ratio, which is the efficiency, what you gain or over what you pay, is the efficiency. And this is what we need to maximize. Again, according to what we need to revise in second law, efficiency of a thermal cycle, like our car engine or gas turbine cycle or water Rankine cycle, efficiency cannot reach 100%. I cannot have 100% convert all heat in the fuel into mechanical work or electricity without rejecting heat. Why? Because in your car engine, you need to throw the exhaust. Why? Because you need fresh air to come instead. Otherwise, you cannot have another cycle of combustion. So that's why you have exhaust. Then you have suction of the fresh air. In the gas turbine, we burn the fuel with fresh air, right? And then after that, we need to exhaust the combustion gases to bring another fresh air. For the steam cycle, it's a closed loop. We don't throw the steam because it is expensive, but we do what? We need to condensate it. Why? Because we need to raise its pressure again, but raising its pressure in the form of vapor with large specific volume will cost a lot of energy, a lot of money. So we condensate it by rejecting this heat and reduce the specific volume, so have a small work. That's why to complete the cycle, start from state one and come back to state one after taking the work, we need to reject heat. That's why this is one main feature, important conclusion of second law. The second point in second law, that we, for each two temperatures, the high temperature at which I add the heat, right, from the combustion, let us say, this is highest temperature, to the temperature I rejected the heat, there is maximum efficiency. The maximum efficiency is usually for the reversible cycle. Reversible cycle that had heat transfer reversibly, had no friction between molecules, had no friction with the surrounding, the boundary of the turbine or blades or shaft. So this cycle was theoretically proposed by Carnot, but it is theoretically acceptable from first law, energy in, energy out, subtraction give you network, but on ground, you cannot have heat transfer without temperature difference, which actually you cannot reverse. Heat transfer from high temperature to low temperature. Can we reverse this without external help? No, like we do in the refrigeration cycle. we give work to the cycle. Then we can transfer heat from low to high. But in reality, or normal situation, like in the boiler, for example, we have the combustion high temperature, maybe 1200, 1300 degree, and give it to the water at 400, 500 degree. So there is a temperature difference. Can you make these delta T zero? So you need infinite surface area, then make your boiler in the area of Hooper or Kingdom or even the universe. What is the meaning of infinity? To have delta T close to zero, to be the cycle reversible, but to have acceptable amount of heat, so you have the area should be infinity, because heat transfer equal area time heat transfer coefficients, I am delta T. If you have delta T close to zero, then area should go to infinity to have a significant heat transfer. So we cannot have a boiler or heat exchanger with surface area infinity. So always when you have heat transfer process in your cycles, it is irreversible. Carnot assume in the paper, I can assume whatever I want. Carnot assumed that I have reversible heat transfer, and he made the analysis and got that eta maximum is 1 minus T low over T high. This gives you a quick idea. Any thermal engine work between T low, very small, and T high, then you have high efficiency. But if you have T low, like you have an engine work in Europe and engine work in Sudan, Europe, T low that at which the ambient can reject the heat is low, and T high is a combustion, same in Sudan and Europe, the combustion temperature will be the same. But the ambient at which you reject the heat in Europe is low and in Sudan is high. So the efficiency of the same device, or in summer and winter, let us say summer and winter, in summer it will perform, in winter it will perform better because the ambient or the temperature you reject the heat is low. We have a question on this point, but I want to spend more time on it. Improve thermal performance, this is what we are going to do to reduce the losses. But as again, we have a cycle, we try to improve it. By example, by raising the T high, we need to raise T high. But there is a material limitation. We need to decrease T low, but there is environment. What is the ambient at which you reject the heat? There are always thermodynamic and also economics, because if you raise T high of your engine, so you have to make your engine from very expensive material to resist the high temperature, right? And this is the economics. So quickly, this presentation of Carnot cycle that have isothermal heat addition, then isentropic expansion on turbine from 2 to 3, then cooling at constant temperature. This can remind you with the condensation in Carnot and Rankine cycle from 3 to 4, from wet region to saturated liquid, 3 to 4. Then isentropic compression and Rankine cycle is by pump, and Carnot and Brighton, it will be by a compressor. So these 4 processes, as you can see, isothermal heat addition, this is how to do it. If we have isentropic compressor, then isentropic turbine, this is the isentropic compression, isentropic expansion, but we have, also isothermal compressor, and then isentropic turbine. This is the 4 processes. This is the heat addition, heat rejection. Actually, the work net is the heat transfer net is the area inside this box, and it is equal to the work net. So Qn, as you can see in this TS diagram, actually presenting or selecting the process diagram depend on what type of process. Like a TS, we use it good if we have isothermal and isentropic process. Why? Because it will be horizontal line for isothermal, vertical line in the isentropic. So the cycle will look nice, and you can get the area, it's the area of a square or rectangle. Anyway, Qn is T high delta S according to definition of entropy. Q out is T low delta S. And then if you divide the work, then this is how simply Carnot constructed his cycle and get the maximum efficiency with the very simple expression, 1 minus T rho over T high temperature here in Kelvin, not in centigrade. Isentropic mean constant entropy, that's why the compression from 4 to 1 have the process S1 equal to S4, and in the expansion S2 equal to S3 in the turbine. Actually, we'll focus here in ideal cycle, but that is have no friction and no irreversibility. Usually in your car engine, you can present it by a closed system where you have piston and cylinder, and the cylinder, the piston is moving with the cylinder, so there is boundary movement or boundary work. The work here is displacement work because the piston is moving. So here, the expansion process or compression, we can present it by BV diagram. So if it is isentropic, it takes this shape, and the area under the curve is the work from integration BdV. And the heat transfer T delta S is Q. So it is, we can represent the area under the curve to give us heat in TS diagram. This is for closed system. There is heat transfer and there is work, but work here is due to boundary movement, displacement of the piston. But for open system like the turbine, the compressors, the pump, we don't have the boundary moving, we have shaft work. We have the shaft rotate. In the pump, we rotate the shaft to push the fluid from inlet to outlet, and the compressor, but for the turbine, we have the gas rotate the shaft itself. In both cases, the work is shaft work. It is actually on BV diagram, it is area left to the curve because it is integration of VdP. This is area left to the curve. And TS diagram, this is the area under the curve as it is. And this is again, this is what we use in open system, VdP for the work, because we have shaft work and we don't have boundary moving. We have only the shaft rotate, and the heat transfer always area under the curve in TS diagram. It is TDS. Right? Now the ideal gas equation, quickly, you have BV equal to RT. This is the ideal gas state equation. You can apply it at any state from beginning of, at the beginning or at the end of a process. A change in internal energy integration of CV dt integration, the enthalpy change in enthalpy is CB integration of CB dt. For ideal gas, you might have different model that assume CV and CP, the specific heat, are constant, are not function of temperature, or if the change of temperature is not high, like in the air conditioning application or something, we can assume CV and CP constant because delta T are not much across the device, so we can take CV and CP outside. So we have this model of delta U equals CV delta T, or delta H equals CP delta T. If we have CP and CP are variable with temperature, so we should know the equation. What is the equation of CP as function of T, and we integrated. We actually, this integration using for delta U or delta H are given in thermodynamic tables that I already uploaded to your Blackboard under the properties. I uploaded the tables. Actually, a number of tables here are referring to the book by Moran and Shapiro that we use in our department, but of course, also your book, the new book you have in your course, is taking some problems even from Moran and Shapiro. It's a very popular book. Regarding the entropy change for gases, it is, if we use CV, dt by dt plus R ln V2 over V1, we take the variation of CV with T, or here the integration of CB dt over T minus R ln P2 over P1. Actually, if a constant specific heat, we'll have these formulas in the left. If it is varying, so better to use the table to get integration of CB dt over T. This part integration is translated to S naught at T2 minus S naught at T1 minus R ln P2 over P1. Now for the case of isentropic relation, delta S will be 0. So we can take either the left, the constant specific heat formula, and get relation between the variation of pressure and temperature from 622 or from 620A. how to get relation between the pressure and temperatures actually for constant specific heat, the left, and constant or variable specific heat. Let us see in the next slide. For constant specific heat, we can get this relation. Actually, if you equate this to 0, then you will have Cp ln T2 over T1 equal to R ln P2 over P1. Then you can remove the ln and you have P2 over P1 equal to some T2 over T1 multiplied by Cp over R. Then you can give this, you can reach to this relation. Here, for constant variable specific heat, you will have this all equal to 0. Then you have R ln P2 over P1 equal to S T2 minus S naught at T1, or ln P2 over P1 will be equal to this delta S naught over R. Then to remove the ln, you need to get the exponential for both sides. Then you will have P2 over P1 equal to exponential of S naught T2 minus S naught T1 over R. Then you can split it. Then you will have what we call P2 over P1 equal to PR2 over PR1. This isentropic process for between initial and final state, and isentropic process with variable specific heat, this is with constant specific heat. Why I focus on this? Because we are going to use them soon when we analyze a Brayton cycle. Actually, we need to, in Brayton cycle, we need to be able to draw PV and TS diagram, at least to understand them. And understand if we see it, or we need to apply mass and energy balance for each component. We need to determine the power output, thermal efficiency, back work ratio. These are important, especially the last part are important things you need to focus, how to calculate it or estimate it for a Brayton cycle. If we have time toward the end of the module, we'll talk about the nozzles and diffusers, because gas turbine is now the main or the engine of aeroplanes or aircrafts. And aircrafts, they have diffusers and nozzles because they convert the thermal energy mainly to thrust or to the jet force. So if we have time, we'll cover it. It is a gas turbine. But let me talk about the ideal gas turbine cycle. So usually used for stationary for power generation, but again, it is used for aircraft, propulsion, marine plants, train. Even we have in Egypt, Dr. Antar knows from Alexandria, we have a train called the Turbine, because it's high speed, so it's used not internal combustion engine, it is used turbine as the engine of the train. Then we have gas turbines are now increasing for large scale. Usually it is used for a small scale or quick power plant construction to produce electricity quickly at crisis, or I mean when you have a shortage in one of the power plant. Actually, this drawing in the left is a very common gas turbine. You take air from the surrounding. This is the compressor. Raise the pressure because you need the fluid at the inlet of the turbine at high pressure, high temperature to be able to push the turbine. So you raise the pressure of the air, normal air from the atmosphere. You raise its pressure by the compressor, then mix it with fuel to give the thermal energy to raise the temperature, then take the exhaust gases at high temperature, high pressure, introduce it to the turbine through a nozzle. Then the turbine will, blades will rotate, give you shaft work. Part of this shaft work, you can go to rotate the compressor, and the remaining in the stationary can rotate electric generator to convert this mechanical energy into electric. In the aeroplane, you introduce the remaining or the exhaust gas with the remaining enthalpy to a nozzle to convert it to thrust. This is a very, yes.
Doctor, Assalamu alaikum. What's the ultimate relation between gas turbines and renewable energy?
Ultimate relation will be in the heat addition here. In the, you can, instead of burning fuel, you can heat the air actually through what we call solar tower. You concentrate the solar energy into a receiver that pass through with air, so you can heat the air to high temperature instead of heating it by burning the fuel.
So we will be having sustainable energy from gas turbine through using through replacing
it is the
fuel.
heating. Yeah, instead of burning fuel, you can heat by solar energy. This is directly related to renewable. Also, there is another type of renewable energy. Instead of burning natural gas or oil like benzene or diesel in the combustion chamber, you can burn, or you have, for example, in biomass, if you have a farm, so you have a solid fuel from the plants, you can make a process called gasification, convert it to gas, and then burn it. This is also sort of renewable. But usually this is common in, if you have a farm like Mara'i or Nada or so, if they have big farm, so you have municipal from the cattle, they can put it in a reactor to convert it into gas by biological technique or by thermal techniques. They convert it into gas, they burn it in a gas turbine instead of natural gas. This is renewable. Or heat by solar, this is also renewable.
Okay.
Okay. You're welcome.
دكتور اسماعيل
Yes.
البرودكتس اللي راح تكون بعد الاكسبانشن في التوربين هي gaseous products.
Actually, after the combustion, if we have a combustion, we have air. This is fresh air coming from the fresh air mixed with the fuel. Then we have combustion gases. The combustion gases, it's yes. Go ahead. Continue question.
بعد الاكسبانشن في التوربين.
بنرميها, it's expansion, exhaust gases. That's why we don't cool it and bring it back to the compressor. We just throw it to the air through the chimney. Yes.
Okay.
That's why it is open cycle. Most of the gas turbine open cycle, like the gas turbine in the aircraft. While you go now up through the stair to your boarding, you see a big fan. This is actually the compressor of the gas turbine. But we'll see it soon in the next slide. But in some situation, if you are using a special gas that, like the one we used to cool some nuclear reactor, we need to cool it. And if we use Rankine cycle, we cool it with liquid water or liquid sodium, and then the sodium heat water. Anyway, or we have a gas, actually we have a gas that cooled the reactor. Then this gas we need to, it is heated by nuclear reaction, expand on the turbine. Of course, this gas might be contaminated with radiation, or it is a special gas. I don't throw it away. So we cool it and return it to the compressor. This is the closed cycle. Or we are heating air by burning coal, for example. So we don't need the air to mix with the coal. So we have a heat exchanger. In the heat addition, we have, but if it is air, we can throw it away and bring fresh air. But as I said, for some special cases, we need to cool, but this is not common. The closed gas turbine is not common. What is common is this open cycle gas turbine. What I want to say for compact, in some gas turbine, maybe old type, the combustion chamber was not to complete part of the gas turbine envelope, but now to make it compact, this combustion chamber became some box here around the shaft. So as you can see, the gas turbine in the aeroplane, it have one casing. You see this engine on the wing, it is one casing. In this, it includes the compressor, the combustion chamber, and the turbine. Actually, to make it that compact, the combustion chamber became part around the shaft. As clear here from this animation, you can see that the air is mixed with the fuel, burn, and then we have the product. As I said, part of the work of the turbine is to rotate the compressor, and this is what happened in the plane. And the remaining power is go for a nozzle to push the plane. But in the stationary, the gas turbine on the ground that we use it to generate electricity, we put electric generator, and usually electric generator is put near the compressor. It is on the same shaft. So it doesn't matter I put it on near the turbine or put it near the compressor. It is rotated by the main shaft, but actually because the turbine is hot, we put it near the compressor, and on the physical ground, we put it near the compressor. It is in this side. Let me show you. This is actually covered with one casing. What typical gas turbine that you see it on the plane, on the wing, when you go with any aircraft now. This is the inlet part, which is the, please, who raised his hand? Can you ask your question?
Yes, Doctor. Just we mean here about the products. We mean the carbon dioxide, isn't it?
It's not only carbon dioxide. This is a very good question. I wanted to talk about it, but I said, let me delay. Okay. Actually, but I will answer you.
Sure.
As you said, at the compressor inlet here, right? This is fresh air. That's why it is air inlet. Then we compress the air to raise its pressure through different stages of the compressor. So you can see here these cans, just like a cylinder put around the shaft, maybe 10, 15, 20, depend on the design of these cylinders, where we have the air come into each cylinder around the shaft. And also we inject the fuel, either natural gas or diesel. They burn it together. This is the combustion chamber. Actually here, this is the combustion chamber is here. This is one cylinder repeated around the shaft. You see another one here, another one here, another one here, around the shaft. These many cylinders or combustion chambers, the small ones around. Then you have here fuel, coming here fuel, and the air coming here. They mix, burn. Then this nozzle have hot gases. These hot gases consist of what? The air is mainly nitrogen and oxygen, right? 21 to 79. This is mainly the percent between oxygen 21% and nitrogen 79%. So it's mostly nitrogen. So when we add the fuel is a small amount of hydrocarbon CXHY, so it is converted to CO2, right, and H2O. But nitrogen will go as it is. So also in the exhaust gas, it's maybe we don't find oxygen, but we will find, because we have lean combustion, we'll find CO2, H2O, but mainly nitrogen as well, because nitrogen is the main inlet. And what is the benefit of nitrogen, subhanAllah, to reduce the temperature? Because if you burn fuel with oxygen only, with pure oxygen, the temperature will go maybe 4,000, 5,000, depending on the fuel, degrees centigrade. What material will withstand this? The presence of nitrogen in the air with this large percent actually like dilution of the combustion or make the temperature in the range of 1,200, 1,500 degrees Celsius. Okay, so if we put more air, so we are going to dilute the combustion. And actually the design of the combustion chamber depends on what material. So you put percentage of the air, the exact amount of air to fuel is in the range of 15 kilogram to each 1 kilogram of fuel. But this gives you the temperature around 2,000 degrees centigrade. To reduce this, so you increase the air, you make the ratio in the gas turbine usually in the ratio of 50 to 1, 50 kilogram of air to 1 kilogram of fuel. So most of the composition of the exhaust gas here will be nitrogen. Most of it will be nitrogen. So its property will be like the air. That's why, to simplify the modeling is a theoretical calculation. You need to make your life simple in the mathematics. So we assume that air is everywhere, from inlet to the compressor, heated in the combustion chamber, and we know here we have chemical reaction, the composition change, thermodynamic property change, and here in the gas turbine we have exhaust gas that have different properties. But since its composition mainly CO2, and if we have excess air, it will be, mainly nitrogen, and we might have oxygen, so the property will be very close to that of air. Not the same, but close. right? And this
Yes, sir,
is
I
the
have a question.
approximation. Yes, you please.
Yes, if we use the nitrogen to run the engine, is it the main problem of nitrogen to cause the metal fatigue, or that's different scenario?
If you use nitrogen only?
Yeah, I mean, like if you use the nitrogen in combustion engines, it will cause the metal fatigue in the engines because it's a hot and cool it down, and the engine increase temperature and cool it down.
No. Actually, nitrogen is natural part of air, right?
Okay.
To have nitrogen alone, you need to separate it from the oxygen, and this is actually need cooling and compression, and we have factories to do this. We have gas factories that separate oxygen from nitrogen for hospitals and for some industrial use to use the nitrogen. But oxygen go to hospitals, for example, and nitrogen mainly for industry, other industry. But why in combustion we need to separate it? We don't need to separate it, right? Because nitrogen does not react with fuel. Will it react with fuel to release or convert its chemical energy into thermal energy? Nitrogen doesn't react.
Yeah,
what react is the oxygen. Yes.
Okay.
So we take the air because it's cheap. It has no price. Air doesn't have price. But if you want to bring oxygen alone, it has a price. Nitrogen alone, it has a price. We cannot use nitrogen alone because it will give us, first of all, it is expensive. Second of all, it is will create a very high temperature, right? We don't need this very high temperature. So the presence of nitrogen in the air actually act as a dilution or reduce the temperature of reaction, right? Because it is getting heat but doesn't react. So I don't introduce nitrogen to cool down. Actually, at the beginning of the combustion, the process, the temperature is not high. The gas turbine take about half an hour or 1 hour to get heated until it reaches steady state. So the heating of the gas turbine actually, or the starting of it, is not sudden, or it go gradually according to the material specification. So to avoid these thermal shocks and other things. But nitrogen here, I don't bring it intentionally. It is part of the air. Like you have your aircraft is flying in the air. Do you imagine that you put bottles of nitrogen or oxygen there to represent a very high weight and very high cost? So just take the air while it is flying, isn't it? So this is the combustion chamber, just quickly, but this is, I think, from GE. This is how we inject the fuel here and the air coming here. And this is the excess air, the extra air. Actually, all this air here for primary, for the combustion or for the reducing the temperature before the turbine blades is coming from the compressor. Like here, this is the, let us say, the air, the primary air come here, then the secondary air come here, some from here come here, then this go to the turbine. This transition actually even is coated with the thermal clay or something to protect, or ceramic to protect the metal of the turbine. As I said, yes.
الفورم اوف الفيول هو liquid ولا gaseous ولا؟
Gas turbines actually can burn, mainly it is natural gas, because natural gas is a very clean, use-friendly, mix very well with the air. When you mix it, two gases, mixing is very easy and very nice. And to have a complete combustion, you need each particle of fuel need its particle from oxygen to react very well and completely, right? In some gas turbine, we use liquid because liquid has more density, so you can Like in the aeroplane, you cannot use natural gas because you might need huge tank, right? So in aeroplane, we use naphtha, which is the liquid fuel. So we have a nozzle. You can see here this nozzle actually to atomize the fuel into small particles. It's like the spray coming liquid at high pressure go into the combustion chamber, which is here. This is surrounded by air at high temperature from the compressor. And you have also the spark or the ignition. Then you have a small particles of the liquid surrounded by gas. It evaporates quickly due to high temperature and burn or reach the combustion. Actually, the design of the burner here, the size of the particle from the atomizer or from the spray will affect, will you have a complete combustion or not? Because the particle, while it's traveling at high speed in the path of flow here, it evaporates, and whatever evaporate react and convert to CO2 and H2O and release heat, right? If the particle is big, it might have a high momentum. It can travel, reach to the end of the combustion zone without complete combustion. And this will represent a problem on because it will convert to soot, and a phenomenon called cooking will happen, that liquid fuel or liquid particle convert into a solid soot or carbon. And this will be deposited on the surface. So usually that's why they provide more air toward the end. If there is a small particles is not completely burned, they add more air, and the air, while it is going here, it is heated more from the combustion. So it meet whatever gases here do two jobs. First, to reduce the temperature of the exhaust gas before the turbine. Second, if there is incomplete combustion to any particle of fuel, it helps it to completely burn, right? So we use both. In some gas turbine, especially stationary gas turbine, you have a dual burner. What is the dual burner do? It has possibility of having liquid or gas. And I have seen this in Goraya power plant. They have dual burners. The burner, actually some accessories help for liquid, some accessories for gas. They are a little different, but the gas turbine combustion chamber have the jet for the, or the nozzle for the gas and the nozzle for the liquid. And they can both work together, or which is available to the plant. So, they have tank for the diesel. If there is a shortage or any problem in the natural gas pipeline, they can use the liquid in the tank. But it has its own problems. I don't want to take the time to talk about technical combustion issues. I have researched in this. I have a lot of information because I visited many power plants, but this class time is short. So we can have more question related technicality in the office hour if you want, or but it's okay to interrupt me whenever you want. You are welcome. Can I continue?
Yes, sure. Thank you.
Again, we have 4 processes, 2 isentropic like Carnot, like Rankine, isentropic compression, isentropic expansion. 2 process of heat addition like Carnot, but not isothermal, but like Rankine, heat addition at constant pressure from the, here in reality we have combustion, but here we'll assume that we are heating the air indirectly. Also heat rejection, in reality, we throw the exhaust gas through the chimney and take fresh air. We take fresh air from here. But we'll assume that if we have the heat rejection by cooling, because actually the exhaust gas, we exhausted at T4, for example, and take air, fresh air at T1. So we assume that what is the heat lost is what m dot gas delta or H enthalpy at 4 minus m dot air enthalpy at 1. Because this is what the difference is what I lost. Actually, but this is the major losses when I throw this heat. This is the major losses in gas turbine, because the temperature here might be 500, 600, 700. Sometimes it reaches 700 and we just throw it to the atmosphere. Actually, approximate, first of all, we know that half of the cycle here, we have fresh air. We have here air, right? and here we have combustion gases. So that have CO2, mainly nitrogen, air mainly nitrogen, oxygen here, mainly nitrogen and CO2 and H2O. But here you will find the percentage of nitrogen is dominant. So we assume that air is through all around. This is our first approximation. Second approximation, as I said, we don't have real cooling, but we have the effect of cooling. Like we exhaust the gas here and take fresh air here. And why? Because by all means, we need oxygen. I cannot take the exhaust gas back, right? Unless we have indirect heating and we are using a special gas. So this is the what actually we assume that we have, instead of combustion, we have heat exchanger to give heat in and we have heat exchanger to give heat out. Okay, this quickly, and this is the actual cycle. Take fresh air, mix it with fuel and combustion, but we represent by heating, and then expand in the gas turbine. As we said, the heat Brayton cycle, we said first assumption in Brayton cycle that we have air throughout. Why air? Because it's mainly nitrogen, either in the compressor side or in the turbine side. Before the combustion chamber and after combustion chamber, the gas mixture is mainly nitrogen. Also, we have imaginary cooling from state 4 to state 1, or from exit to the turbine to inlet to the compressor. We have imaginary cooling. This is Brayton. In real cycle, gas turbine cycle, it doesn't have this cooling heat exchange. These are the equation we are going to apply, which is the first law in steady state, steady flow process. We need to apply it for each component. The general formula is Q dot minus work dot equal to summation of M exit, H exit plus kinetic potential at the exit minus M inlet time, H enthalpy kinetic potential at the inlet. Of course, most of the component in the cycle is one inlet, one exit. You see the compressor, one inlet, one exit. Combustion chamber is one inlet, or heat exchanger at high temperature, one inlet, one exit. Turbine, one inlet, one exit. So we don't need the summation sign, and we neglect the kinetic and potential changes. So we have Q dot minus work dot equal M dot exit, H exit minus M dot H inlet. So since M dot is fixed, so closed loop, so M exit equal M inlet, we call it just M. This is the formula we are going to use. But when we apply it for compressors, we don't have heat for compressor, but we have work for compressor and turbine. For the heat exchanger, we don't have work, but we have heat added or heat rejected. So this is the what we do. This is the 4 cycles. Again, when we just apply the first law is work net equal Q in minus Q out. This is the 4 processes. Isentropic work in the compressor from 1 to 2, then 2 to 3 is the heat addition at constant pressure in the heat exchanger or combustion chamber. 3 to 4 expansion in the turbine. 4 to 1 is the heat rejection, but actually we exhaust the gases at 4 and we take fresh air. This line from 4 to 1 should be a dotted line. So the heat addition minus heat rejection give us the area inside the cycle, which is equal to the network. So what is the efficiency is network, which is Q in minus Q out over Q in. So if we simplify, it will be 1 minus Q out over Q in. Q in is HC minus H2. If constant specific heat, if this constant, we can take it out, CP out. It is integration actually, CP delta T, but we can put it this way. Then we have eta thermal is 1 minus, we can put this formula in terms of temperature. I want just to comment here something on science and engineering, the first slide I put. From the properties of gases and the constant pressure line on TS diagram, we notice that always you see here difference between, actually here also it can be H, because if we multiply it by just CP, then this temperature will be enthalpy. The constant pressure lines, if you see here delta H here between 1 and 2 is less than 3 and 4. Why? Because the pressure lines, as the temperature go down, they converge, they come close to each other. By this is physical phenomena. So That's why we need to compress at low temperature. We need to compress at what? At low temperature. So if I have my cycle work at very low temperature environment, then the compressor will take place here. You saw this amount of work of the compressor will be much smaller than the work here of the turbine. This is work of the turbine. It will be, if we cool more, we have less work here. Is this only the reason? No, I will talk about another reason that you remember the shape of the gas turbine. Oh, so sorry. When we build the gas turbine, it has a fixed size, isn't it? What is the flow rate here that this compressor can suck? It is the volume of the space between the shaft or the blade and the casing. This is the volume that I will suck for each revolution, multiplied by number of revolution, give me the volume flow rate, multiplied by density of the air at the inlet, give us the mass flow rate. Give us what? The mass flow rate. Just I built the gas turbine, the mass flow rate of the air will depend on what? On the density, because it is what? It is mass time volume flow rate. Volume flow rate, fix it, regardless you run it at cold space or hot space, the mass flow rate, volume flow rate is fixed, because it's the volume, geometrical volume multiplied by number of revolution, that is the design one, then multiplied by density. Density depend on it is cold air or hot air, or cold gas or cold fluid, or this specific volume or density, right? That's why if I'm talking about gas now, so if the density of the gas is B over RT, this is the density of the gas, P over RT. So if we have the temperature low, we have high density. If it is high, I mean the temperature high, we have low density. So the cooler the air, we have two things happens. From this graph, the specific volume is small, so the work is integrated and VDB is less. Also, the mass flow rate is higher. So we have the work, specific work is small, and the mass flow rate is high. Why we need the mass flow rate? Because we said in the combustion, we need for each kilogram of fuel, we need 50 kilogram of air. So if I have in the design condition, I design my turbine at 15 degrees, this is the ISO condition, I make the design for 15 degrees Celsius. So the mass flow rate, for this mass flow rate of the air, I can burn this mass of fuel. But if the density change, the air become hot. So the air will be less, the mass of the air will be less. So I cannot inject all this fuel that was for the design. Why? Because I injected, I will not have enough air. If we don't have enough air, so part of the fuel will not burn. What it will do, due to high temperature, it doesn't find oxygen, so it will be converted to coke. And this coke will deposit or soot will deposit on the blade to create more problems. So I will not take the energy from it, and it will create problems. So that's why the gas turbine designed at ISO condition, which is 15 degrees Celsius and atmospheric pressure at the inlet, will not give its power. Why? Because the control system feel if the air temperature is low, okay, I give the fuel I designed for. If the temperature is high, I reduce the fuel such that I give fuel enough to the air. Otherwise, it will create problem. So you have a gas turbine that you cannot burn the design fuel, so it will give you less power, okay? Because I have question on this in there. Anyway, if we have a constant specific heat, we can reach the efficiency by constant specific heat relation for isentropic process. So the efficiency will be this way, eta thermal. This is the actual efficiency of gas turbine if it is isentropic compression. and isentropic expansion. It is 1 minus R over pressure ratio. RB is the pressure ratio, or P3 over P4 or P2 over P1 to the power K minus 1 over K. K here is the specific heat ratio, or Cp over Cv for the gas if it is constant properties. So actually the efficiency of the cycle depends on the pressure ratio of the compressor. So if you have the pressure ratio, this is show you how is the efficiency depend on the ideal cycle, Brighton cycle, that has constant specific heat. So they are saying the ideal here, the pressure ratio is around 11. Why? Because the higher the pressure in the compressor, mean you buy larger compressor, more expensive, but more important is the material strengths. You better not to have very high pressure, right? Because of the material of the blades and casing and other things. Right, but to make simple analysis for each device, as I said, Q dot minus work dot equal M dot delta H. For turbine, we don't have Q, so work turbine is H exit minus H inlet. For the compressor also, we don't have, we assume insulated, so work compressor is H exit minus. Now we take the absolute value, forget about the sign, we take always positive, but we know work turbine is positive because it is out, work compressor is negative because it is in, but we put here positive values. Heat added is Q dot minus work dot equal delta H for the heat exchanger here, but we don't have work, so Qn is delta H. Q out is also for the imaginary heat exchanger here. That's why I put it dotted, because it is reality is just not there. But this is the heat we lose. So efficiency is, as I said, work net over Q added, or net heat Qn minus Q out also will work. There is something important called back work ratio, is how much is the work of compressor compared to the work of the turbine. If this ratio is high, mean I'm taking less work, but if it is low, mean I have a good cycle. That's why the work ratio here, if we go back, the work ratio, if I work my cycle at high temperature, if I have hot environment and my cycle the inlet start at high temperature like a summer day, so this will be the work of compressor, and the back work ratio will be high, the work of compressor of work turbine. But if I am at low in winter days, and this is the work of the compressor, this will give us back work ratio less than at high temperature days. That's why even in Goraya power plant, they have combined cycle, that is gas turbine and the steam turbine. The gas turbine designed to give 180 megawatt in winter days or at 15 degree. But in summer, when the temperature reach more than 45 degree, the gas turbine give only 120 megawatt. They lose 60 megawatt. They lose 60 megawatt. Why? Because the compressor suck the volume flow rate as it does in winter. In summer and winter, volume flow rate the same. But in summer, the density is low. So they cannot introduce the fuel that they can burn in winter. They introduce less fuel. So this less fuel give less power. How much reduction? 30%. I have a paper in this. I put it in your Blackboard in module 4. I put a paper related to the effect of inlet gas turbine cooling, because people in Saudi are clever. We have clever engineers. In Mecca, they start to cool the air inlet by using ice. In some other places, they spray water to make evaporative cooling. In some other places, they put like air conditioning system. And what I did in the paper, we compare different techniques. What is the effect of cooling the air at the inlet? Of course, it will increase the power, and power is money that I produced. But whatever accessory as I added at the inlet, it is cost also. So you have to study the economics of your project. This will improve the efficiency, reduce the fuel, improve the environment, give me more power, but also I will pay more at the beginning. So you need to compare. If you have net profit, you go ahead. If you don't have net profit, you don't do it. I will go.
Allow me, Dr. Ismail.
Yes.
Sorry for the interruption, but I think that the guys may need a little bit of a break. It's
Okay.
like 1 hour, 15 minutes. So
we can stop for how long? 10 minutes?
It's all up to you. That's fine if you wish.
Yeah, 15 minutes will be enough because I want to give them example. So we can stop for 15 minutes and I'll go a little faster, but it's okay. يا شباب.
Okay, doctor.
Yeah, great.
Yeah, I was planning actually to stop at 2. Okay.
Now it's 2.
Right. Thank you.
Doctor, excuse me.
Yes.
What's the difference between the Brightman cycle that we have studied now and the car engine?
Car engine is the actually is the structure. We don't have the turbine. Actually, the car engine, as you said, as we said at the beginning, is a piston and cylinder. You have the piston, a cylinder inside it, the piston that have inlet valve and exhaust valve, and you have the piston is connected to a crankshaft that rotate in a circle, but is connected, but what we call it connecting rod. So when we have a starter, we turn on the starter of the car by the battery, the crankshaft rotate and pull the piston down, allowing the intake valve to suck the air and the fuel. Then you compress it due to rotation. It compress again, so the two valves closed, and then you have the spark, like in auto cycle. Then it burn due to combustion. This produce gas. It has at high temperature, so it expand, pushing the piston to add more power to your cycle. And of course, the starter is separated. So you have the operation, most of the operation here in a piston cylinder, like a closed system. But if you look in the, you have suction, suck fresh air, then compress it. This is the compressing process. So you have the combustion at constant volume, not constant temperature, like we have here in gas turbine. The combustion here happen at constant volume. Then you have expansion, right? Then you have exhaust or you have cooling. So there is some similarity in some issues, some different in some issues. So this cycle basically is the ideal cycle for engine that use benzene, or you call it auto cycle. You have the compression, we call it maybe isentropic, then combustion or the heat addition at constant volume. Then you have isentropic expansion also. Then you have the cooling, which is maybe constant pressure to close the cycle. If we have another fuel, which is diesel, which is a bit different, that you have the compression, isentropic, then the combustion is at constant pressure, then you have the expansion again. I mean, internal combustion engine, we are teaching in our course, in undergraduate second thermodynamic course. I can share with you the principal cycles, I mean the modeling cycles. But again, the main difference between the car engine and the gas turbine, that in the car, the process happen in a closed system, relatively closed system with boundary moving. The work is done or taken by moving the boundary or moving the piston. Here, we have basically open devices. We don't have inlet and outlet. The flow, the fluid go actually from different devices. You have compressor, you have combustion chamber, you have turbine. There we have only piston and cylinder, and everything happen inside. Okay. There we apply the work based on integration PDV. Here we have open devices, work an open system, and we have the work, especially shaft work, is we calculated from integration VDP, or area lift to the curve. So basically, two different systems, two different mechanisms. But the thermodynamic process, there is some similarity in the thermodynamic process, like the compression, isentropic, adding heat at constant pressure, expansion. But as it, the main difference is the work in the car engine due to displacement work or boundary movement, which is the piston movement. Here we have shaft work due to the rotation of the turbine blades or the blades of the compressor, right?
Yes, right, Doctor. Thank you.
You're welcome. يا شباب السلام عليكم. Should we resume? Hello?
وعليكم السلام دكتور.
Yes, doctor.
خلاص. Just I got a question in the break. Maybe some of you heard it, some didn't. One of your colleague asked, what is the difference between this gas turbine and our car engine? I said that the main difference is that in the car engine, it's a piston and cylinder, and the work we added in the compression stroke or in the work we take in the expansion stroke is done due to the motion of the piston. And it's a boundary motion, right? Moving boundary, and the work is integration PDV, the area under the curve in PV diagram. This is first different. Second, it is a closed system with moving boundary. Here in the gas turbine, we have an open device with no boundary moving, but we have shaft work. So in the shaft work is left to the graph in BV diagram, and it is open system, not a closed system. In the internal combustion, it's everything, all the thermodynamic process happen inside the space between the piston and cylinder. It's a closed chamber, closed system, right? The thermodynamic cycle of compression, heat addition, and expansion again of the piston is all in closed system. The exhaust, we open the valve to exhaust, and this is the cooling, and it is imaginary. So the compression and expansion, we might say isentropic. For a spark ignition engine, the heat addition is constant volume. In diesel engine, the heat addition might be constant pressure. But anyway, the main difference between gas turbine and diesel engine, this is diesel internal combustion engine is a closed system process, cycle in a closed system. But here we have a cycle in open systems. We have the compressor is open system, has inlet and outlet all the time. Combustion chamber has inlet and outlet all the time. Turbine has inlet and outlet all the time, and all devices work together simultaneously. Now I have just a cartoon to stress this point that work in compressor and a turbine is integration VDP in turbine cycle, because this is the open system or shaft work. As you can see here, the compression is from 1 to 2, from low pressure to high pressure. And the area left to the graph, which is shaded here in this cartoon, is give you the work of compression. But the expansion is the process from 3 to 4, and the area left to the curve 3 to 4 give us the expansion work. And you can see it is more than the compression work. It's the difference between work and turbine that we take it positive, minus the work we paid in the compressor, which is negative, give us the net work, which is the area in the cycle as shown in this shaded area in the cartoon. So, but to take this more work in the turbine, we should have raised the temperature, because the expansion at high temperature gave us more work. The compression at low temperature gave us less work. That's why we compress at low temperature, we expand at high temperature. This is the science part. We learn it from the properties of gases. And this is the engineering. When we built the cycle, we made the compression at low temperature and expansion at high temperature. This is the engineering. But to raise the temperature, we have to pay heat. Where is the heat we pay? It is the heat from 2 to 3. Usually the work we presented in BV diagram, because area left to the curve, integration VDP. So better to present the cycle on BV diagram. To the area inside the cycle here give us net work, but it is equal to net heat. Do we need to represent the heat in TS? Yeah, if we want, we present the heat in TS diagram. The heating is from 2 to 3, and this is the heat addition area under the curve in TS diagram. It is integration TDS. Heat rejection is from 4 to 1, and the area under the curve 4 to 1 give us the heat rejection. Integration TDS from 4 to 1. if I subtract area under curve 2 to 3, I subtracted from it the area under the curve 4 to 1, give us the net heat, which is the area inside the cycle as shaded here. This net heat in TS diagram inside the cycle give us the net heat, which is equivalent to the net work on BV diagram. As again, to remind you, when we talk about heat, better to present the cycle on TS or process in TS diagram. If we talk about work, it's better to present the cycle or process in BV diagram. But again, the area inside the cycle from kilojoule point of view is the same, either it is a cycle on BV diagram or a cycle on TS diagram. Remember that we just present here the process without a scale, but we do have a chart that has a scale. Now we study quickly the effect of the compression ratio. As we said, from the beginning, as I said, if I start the compression at low temperature, I consume less work. But if I start the expansion at high temperature, I take more work, right? But the limitation of the high temperature, which is T3, is the material limitation, because when you burn at very high temperature, then you might get the blades of the turbine damaged. That's why in the turbine blades of the aeroplane or aircraft, we cool the blades. Even in some turbine on ground, we take some air from the compressor to cool the blade from internally. It has a complicated design, the cooling system, but we should cool it from internally, just to make the material live longer. Now we have seen, you remember the efficiency, thermal efficiency is 1 minus for Brayton cycle, 1 minus 1 over the pressure ratio to the power gamma minus 1 over gamma, or K minus 1 over K. K or gamma here is Cp over Cv. And it is in the, for air, it is 1.4 if it is, we talk about constant properties. This means that we increase the pressure ratio, we increase the efficiency. We increase the efficiency. But what happened if we increase the compression ratio from 1 to 2, and instead of 1 to 2 here in my drawing here, we compress up to 2 prime. This means we'll have more temperature out of the compressor. First of all, we need to buy a larger compressor, or the compressor have more stages. This means more cost. It gives us the temperature before the combustion chamber 2 prime is high. Then we expect out of the combustion chamber for the same fuel amount, we give a high temperature, T3 is high. So we expect more work. That's why the area of the cycle here, the area inside the cycle is more. But what is the limitation? The limitation, as I said, is the material limitation. Always these metals at high pressure, high temperature, its resistance get less. So increase the temperature and also increase the pressure, the stress is high. So as we said, this is the graph of eta thermal with the pressure ratio. The higher the pressure ratio, the higher the efficiency. But as I said, we limit ourselves by temperature T3 prime, because this is might deteriorate the blades. Now, if we fix it T3, because this is the limit from material people, they said don't increase T3. How? If I increase T2, the outlet of the compressor, T3 will increase because of the same amount of fuel. So we tell you, add more air to reduce the temperature. This secondary air, we have seen I talk about after in the combustion chamber, we add more air from these holes you have seen in the drawing. Then for same fuel, we added more air, so it will keep the temperature, because at the inlet, we increased T2, but if we added more air with the same fuel, which means same power, you have more mass of the exhaust gases, but at lower temperature, lower enthalpy, but you increase the mass time enthalpy, then the total power is the same. So for pressure ratio 2, you will have this cycle look like this. I mean, the first rectangle like down here, that is have this area, but if you increase the pressure ratio, the same T3, either you have a thin box or he's high pressure, but still less power. So here, efficiency will increase with the pressure ratio, but the amount of work, which is work net, will be affected because it is related to the area inside this box. When you increase the pressure with fixed temperature, maybe you will have less work. If you increase the pressure, less net work, because the compressor work increases. And now here, if you make it very high pressure, you might find the expansion on the turbine equal to the compression work in the, and work net becomes small. So we have another judgment, which is we calculate the specific work. As you can see here, the area here of this low pressure box is more than the high pressure box. So in between, there is an optimum pressure ratio. So I got this derivation actually from, we used to do it. Remember, the proper air to fuel ratio is 50. This we talk for each kilogram of fuel, we need to put 50 kilogram of air. If we, due to the temperature, this air is getting less, then I should inject less fuel to keep this ratio fixed, Again, just a quick here, the compressor work to turbine work is called back work ratio. In the steam turbine, the work of the compression is through pump, and the work in the pump VDP is very small. That's why the specific volume of the steam is the turbine, steam turbine can be smaller compared to gas turbine. Okay, so this is the turbine itself. But the plant, the steam power plant, listen here, when I talk about turbine, when I talk about the plant. Turbine, I talk about the turbine part only, this part. Sorry, what happened? Yeah, when I talk about turbine unit, I'm talking about this part only, right? I'm talking about this, not about the plant. Plant is all this. And you know, in the gas turbine, this combustion is around the shaft. So it is very compact. But the turbine here, when I talk about the turbine, for gas turbine, for the same power, let us say 100 megawatt, steam turbine might be smaller because the enthalpy content in the steam is higher than enthalpy content in the air due to the a lot of things. Steam have latent heat already stored in it, air doesn't. It's have only sensible heat. So what I want to say here, that I can use here a small mass flow rate with the same power for steam, but for air I need larger. But the plant, for the steam power plant, the plant is much bigger because of the steam generator, the boiler and the superheater and everything is much bigger in size compared to the combustion chamber here. So when we talk about plant, the steam turbine power plant size is big. But the turbine itself for same power for gas turbine is bigger, but the total plant or the gas turbine cycle is smaller than a steam power cycle. Let me just jump to the slide. So we talk about the specific work, which is work turbine minus work compressor. This is the efficiency. We have done it for constant specific heat. We have this efficiency relation, 1 minus 1 over C. And remember, C is the pressure ratio to the power gamma minus 1 over gamma, or K minus 1 over K. Gamma or K is used for CP over CV, right? This for constant specific heat. For variable specific heat, we use the enthalpy from tables. But the specific work, which is CP T3 minus T4, work turbine minus work compressor, if we take it constant specific heat, we might reach to this formula. As you can see here, we have a small t, which is T3 over T1, or the maximum temperature over inlet temperature. And we have C the compression ratio to the power gamma minus 1 over gamma, or K minus 1 over K. So this tell you that the change of the pressure ratio, or it increase the pressure ratio, might reduce the specific work. Increase the temperature, increase the specific work. But we know that C and T are related, so there is an optimum value. So if we differentiate this equation with respect to T, or with respect to C, the compression ratio, we can get and equate it to 0, we get the value of C that give us optimum or maximum or minimum specific work. So this is actually the drawing done, how the efficiency increase with the pressure ratio, how the specific work vary with the pressure ratio. At low T to T3 to T1, which is 2 here, yani T3 out of the combustion chamber is double that of the inlet to the compressor, or treble or quadruple or 5th time. You can see here that the specific work increase to a maximum, then decrease, increase to a maximum, then decrease, increase to a maximum, then decrease. But at higher temperature ratio, if you increase the temperature by more combustion, then the pressure ratio doesn't affect much. But usually the T3 over T1 is in the range of 4, and you find here the optimum pressure ratio is 11. This is the justification here. T3 over T1 equal to 4 is material limitation, because of high temperature we don't increase it much, and the pressure ratio we take it at the maximum specific work, because you don't need to build a turbine plant that give you highest efficiency but very small work. So you need to dig it with reasonable efficiency but enough work. Because when we build a power plant, what is important to us is the amount of work it gives. Like if I build a gas turbine that give me 180 megawatt in winter, and then it give me 120 megawatt in summer. In summer, I have the air conditioning need and the cooling requirement is needed more in summer, but the gas turbine, the power plant give me less power. Then this is a problem. Either I have to install another turbine that give me the 60 megawatt, and this will cost a lot money and time to build another power plant, or to cool the inlet air anyway. But efficiency here is not important to me. Important to me is I produce the power needed to satisfy my city or my town. Okay. This is the irreversibility. As we said, compression always has friction between gas molecules and between the gas and the plates and shaft and other things. So the compression will take more work, and expansion will give less work due to irreversibility. So when we take actual cycle efficiency, we take the actual work. And I think Dr. Antar talked to you about ETA compressor and the ETA turbine, or ETA isentropic for pump and turbine, and it is the same here. Okay. We wrote here the ETA turbine and the ETA compressor isentropic, similar to the pump and turbine. As we said, when we have a high temperature or high compression ratio, we get the high temperature of the combustion, and the exhaust will be also at high temperature. That's why we might have regeneration or combined cycle to reduce the heat loss, because the most part of the losses in the gas turbine is the exhaust gases. Usually we throw the gases to the ambient at high temperature. To make use of this, either to heat the air after the compressor, or we take this exhaust heat to boil water and install Rankine cycle. If we take the heat to heat water and build Rankine cycle, we say we have a combined cycle, gas turbine plus steam turbine. Or regeneration, that we take the exhaust heat to heat the air after the compressor. This is called regeneration. We keep the heat inside our cycle. We try to keep the heat inside our cycle. I have a quick question here. For regeneration, can we heat the air before the compressor? Anyone? Answer. I'll give bonus.
Yes.
Do better in regeneration cycle. I said we heat after the compressor. Can we heat before the compressor is better?
If you heat before, you will increase the work of the compressor.
would increase the work and reduce the density. So it's not recommended to heat the air before the compressor. We heat it after. Who answered?
Ahmed Ibrahim, myself.
Ahmed, خلاص Ahmed Ibrahim, send me email or and CC to Dr. Amtar so we can add bonus for you.
Okay.
1%.
Okay.
Right. Now we have now example that a simple Brighton cycle, we need to calculate its efficiency, and I want to work this example step by step with you. Right? So first of all, let us read. It's a Brighton gas turbine cycle, operates with isentropic compression and expansion, as shown in the TS diagram. Air entered the compressor at 95, not 1 atmospheric pressure. It is 95 kilopascal, which I put here converted to you into megapascal because I want to use computer-aided tables. Of course, here to solve this problem, we can use either constant specific heat or we use variable specific heat. If we use constant specific heat, we had the formula for the efficiency that depend on the pressure issue, or we can use a variable specific heat that we need to use delta H or Q in minus Q out over Q in. Now let us read why I put in megapascal, because I want to use computer aided tables that Dr. Amtar provide the link to you in Blackboard. I'll share my screen with you to how to solve using or to get the properties using CAT, computer aided tables, or use thermodynamic tables that also I shared it with you. Now, and the ambient temperature, this is at the inlet, which is 295 Kelvin or 22 degrees Celsius. The compressor has a pressure ratio of 6:1, yani exit pressure P2 over P1 equals 6/1, or P2 6 times P1. Now, if I have B1.095, how much is B2, the outlet of the compressor?
S1 is equal to S2.
Huh?
S1 is equal to S2.
No, I have I have the inlet pressure B1.095 Pascal.
Multiple in 6.
Yeah, multiplied by 6. So this is, he said B2 over P1. This is information he gave.
Okay.
He gave it. I'm just translating here what I tell my students. When we read the problem, first of all, we needed to understand. Then second step is to translate the English in the problem into thermodynamic information. This is English information, and then we translate it into thermodynamic information or simple equations, right? So he said pressure ratio, it is P2 over P1 equal what? 6. He gave me P1. So from this equation, I can get P2, right? Now, when I ask you what is T2, if you have T1, 295 Kelvin, I ask about T2, you come to the other. Oh, what is the process? It is isentropic. What is the relation between T2 and T1? I have either way, constant properties, so T2 over T1 equal P2 over P1 to the power K minus 1 over K. Come here, that S2 equal to S1. Either I use the constant property model or I use variable property model, okay? Constant property model give me this equation, T2 over T1 equal P2 over P1 to the power K minus 1 over K, right? He gave me here T2, no, he gave me P2, P1 and B2 over P1. What is the temperature at T3? He gave 1100 Kelvin or 82.7 degrees centigrade. Now I want to just end the show here and bring the cycle drawing on TS diagram. So I want to take this drawing with me to here. you see this modification I'm doing now, I will reflect it on the presentation. So that's why I will update it after I finish the class, right? So what we need to do, ya shabab, to calculate the efficiency, simply we need to get Qn. This is the heat N. Minus Q out. Okay. If I got Qn, how I get it? It is H3 minus H2, right? What is Q out? H4 minus H1. So I have state 3 given. He gave it. State 1 given. But state 2, I need to find it. State 4, I need to find it. I need to get H1, H2, H3, H4. Actually, H3 minus H2, I can get H3 directly from the table. H2, I need to find it out based on constant entropy, as someone told. And H4, I got it also expansion isentropic. Yes.
عذرا عن المقاطعة. ما فهمت فيك نقطة الإيماجينري هيت اكسشينجر.
Let me explain it very well. Now, as we agreed, the gas turbine depend on, or any heat engine depend on taking heat from high temperature source, right? And make it do work. Take a fluid, give it heat at high temperature source, and make it do work, right? We do this how? In the gas turbine or even in your internal combustion engine, you burn fuel, so you convert the chemical energy into thermal energy, right or wrong?
Right.
Right. Now, to burn the fuel, we need what?
Fuel. Air.
And oxygen, right? We need oxidizer and fuel. Here's the oxidizers that very cheap and available, especially in the aircraft, is the air, right? Because air includes oxygen. So each time, because this is continuous operation, I inject the fuel, I have air. I inject the fuel, I need air. So this is a continuous operation, right? So we suck the air, but we need this high thermal energy. We need it to be at high pressure to be able to push, because we need these hot gases to push the turbine blades. So we need it at high pressure. That's why we need a compressor, right? But the basic idea here, what I need is air, which is oxidizer, to make it high pressure to make it able to push, right? So we need to suck the air to force it inside the combustion chamber. So we need always fresh air here. We need always fresh air down here. Sorry. We need fresh air here, always. Right, this is state 1. Now I take the air, I compress it, raise its pressure, give it heat here, directly or indirectly. Then I have at state 3 here, air at high pressure, high temperature. It rotates the turbine and it loses its thrust or power, or pressure. It loses power, of course, but it came here at low pressure, right? I exhaust it. I throw it away. I don't need it. Because, why? Because it doesn't have oxygen. It has CO2, nitrogen mainly, but it doesn't have, and it's still at high temperature. At high temperature, if it is a very expensive gas, so I need to cool it down. I don't want to throw it away. I need to cool it down, because here, if I get it high temperature, I will consume more work here in the compressor, isn't it? It is at low pressure, but high temperature. So principally speaking, or Brighton imagine that I need to cool it to bring it to state 1 to complete the cycle. This is to complete the cycle. I have gas here at low pressure. I need to raise its pressure here from 1. I need to suck it here, but I need it at low temperature. Why? To reduce the work of the compressor. So I have to cool it down. This is the cycle proposed by Bright, especially if we have here expensive gas, right? But we have air. So why I should cool down the exhaust gas that doesn't have oxygen? I threw it away. That's why we say it's imaginary. Why imaginary? Because when I threw these gases in the chimney, it is at high temperature, but when I suck fresh air, I suck it at the same condition, low temperature at 1, isn't it? So the imaginary situation here that we assume that this air mixed with the surrounding air, cooled by the surrounding air, and then we have this, because the air is very huge, the real air surrounding the plant is very huge. If you imagine that this small stream of gases coming out, mix it with the air and cool down, then this is imaginary cooling, isn't it? But in reality it's not. I'm not really cooling in a heat exchanger and this and that. I'm not taking the same air particles that I cooled it down. Do we? Thermodynamically, I always take the fresh air here at the same state 1. And I exhaust here. This process from thermodynamic point of view, as if I take this amount of gases, because the mass flow rate is fixed. Even you've added mass, imagine you added 50 kilogram of air and 1 kilogram of fuel. What is the mass here of gases? 51. If you assume it is 50, will make a big difference for you? 51, you approximate 51 to 50. Will it make difference? It's very good approximation just to simplify your life. But of course, you can make the balance, that is 51. But actually, this 51, I don't take it back. I take another 50 here at 1. So I'm assuming that we cooled, but the effect from thermodynamic point of view is cooling, as if I am cooling this 50 kilogram back, I bring it back to 1. But in reality, we throw it. Why? Because it doesn't have oxygen. You understand now why I'm calling imaginary cooling, imaginary heat exchanger?
نعم دكتور شكرا لك.
Barakallah fik. So let us now go. First of all, we can calculate the efficiency here. I said Q in minus Q out over Q in. Q in is H3 minus H2, and Q out is H4 minus H1. Right? So we need to get H1, H2, H3, and H4. H1 and H3 from table or whatever, I have it given because he gave the temperature and pressure for the 2 states. He gave the temperature at 1 and 3. So we can get enthalpy of air at 1 and 3 from thermodynamic table. But what about 2 and 4? So we need to apply isentropic relation, as your colleague said at the beginning of the problem. We have isentropic relation, S1 equal to S2 and S4 equal to S3. This is a key, right? But do we know, if we assume that the specific heat constant, can we use the formula? Efficiency of the thermal cycle 1 minus 1 over C, and C is the pressure ratio to the power K minus 1 over K. Can you calculate it based on this? Shabab, can you calculate this cycle efficiency based on the constant pressure ratio, constant specific heat, and get from the pressure ratio here from this formula? Because this formula, we drive it for efficiency of Brighton cycle if the specific heat is constant. Can we use this? Let me use this and do it together in Excel. I like to use Excel a lot. So let us try to follow with me. I just put the formula here to remind me what I want to do. This is the pressure ratio, RP. They said it is 6. And comma for air is K, or a specific heat. For air with constant property is 1.4. So what is efficiency here? H, make it symbolic to look efficiency. Oh, sorry.
Doctor, how did you know that air is constant?
I assumed, this is what Brighton assumed, that we have, as I said, half of the cycle have air in the compressor and into the combustion chamber. During the combustion chamber, we have added the fuels, then we have exhaust gas. Properties of exhaust gas is similar to that of the air because mostly it is nitrogen, either air or exhaust gas. So we assume it is air throughout, right? The second thing, we know that the air properties will vary with temperature, the specific heat will vary with the temperature, especially if the difference in temperature is high. And this is true in the gas turbine situation. But to simplify the life, we assume specific heat constant. So we got this formula for a specific heat to give us a quick calculation. How much is the efficiency expected based on this pressure ratio and based on how much is the efficiency. This is a quick estimation, but exact estimation we'll do it together with variable specific heat, okay?
Okay, so in
we can
Brighton,
assume Brighton with constant specific heat efficiency is depend on the pressure ratio only. So the efficiency here will equal to what from this formula is 1 minus open bracket 1 over R with the pressure ratios here, but it is to the power what? K minus 1 all this over K. Where is K? Here. What is the efficiency? Sorry, I should divide here, this one. What is the efficiency? About 40%. Let me make big. Sorry. So the efficiency here is about 40%. Okay, if we multiply by 100, just to make it percent. Sorry. Oh, sorry. It is 40% time 100. It's 40.1%. Okay. If
Doctor,
we use,
how did you know? How did we know the values of K and RP?
Yeah, this is what was experience. I'll show you in the thermodynamic table soon. But of course, I don't know, maybe some of you background is electric engineering, some of you didn't take thermodynamics, so I'm sorry for this, but pressure ratio it is given, right? In the problem, this RP is given in the problem.
Which is P2, right?
P2 over P1. Is given in the problem. Okay. This is given in your problem. I was giving the pressure ratio. Remember here, he said it is 6:2. Khalas?
Yep, clear.
The assumption of a specific heat constant is an assumption, not real. But usually engineers make a rough estimate. And for example, he said, now if you are in a tender and you are evaluating the cost of a project and you said it is about 1 million, right? To take the tender, right? And then when you made the calculation, you find it 1,002,000 or 1,005,000 or 1,050,000. Still what you did is a good approximation, isn't it? You understand? So when we make engineering assumption, that doesn't deteriorate the calculation or by wrong assumption, but it is give me a good idea where we are. To prove this, I want to share with you how to use the thermodynamic tables. This is the thermodynamic table I put for you on the blackboard.
Doctor, cannot we use the website?
Yeah, I'll use the website. But as I told you, sorry, We'll use the website together. I'll just, anyway, these thermodynamic tables, it has, I don't know why it is not showing. Are you seeing my screen? Why the table are not coming? So sorry for that. My browser is not working properly. But let us use the variable properties. I'll use the cat, or you can use a website, but as Dr. Antar pointed before, that it might not be that accurate for the properties, but it doesn't matter. I want to show how to use variable properties. And this is the CAT, the thermodynamic computer-aided thermodynamic tables. You have this software, you can install it in your laptop and you can use it.
We're not
Yes.
able to install it, Dr. Maybe it's for Windows only.
Maybe, but we can use the website still, but I don't know. I tried to use the website yesterday, but I think there is a problem to make the process, or to usually.
You mean, the doctor, just for me to get in that, you mean thermodynamic calculator?
Thermodynamic calculators that provided by Dr. Antar in Blackboard.
Okay. Yes, yes, we used it at the website. Yes, I used it.
Yes.
Yes.
We can use it, but as again, as I told you, to get the properties, we have for any fluid 6 properties, which is pressure, temperature, enthalpy, entropy, internal energy, and specific volume. This usually is the 6 properties we need. To get in these 6 properties, you need at least 2. Like in the chart, you need X and Y to locate a point. In the table, you need a column and row also to locate a point. So always you need 2 properties, right?
Yes.
Here for the isentropic process with the variable specific heat, we'll use what is given the pressure or temperature and PR. PR that relate state 2 to state 1 in the compressor and relate state 4 to state 3 in the turbine. We'll use a PR, the pressure, reduce the pressure. The reduced pressure is P2 over P1 in the compressor, and it is P3 over P4 in the turbine.
Okay, so
for isentropic process. So let me show you how to use it in the computer-aided tables. Maybe if you need, I'll show it also in the thermodynamic tables, the PDF file.
Okay.
Okay. To use these computer-aided tables or any, first of all, you need to make sure about the units you want to use. The units you want to use. It is clear for us here, it's a temperature in centigrade, pressure in megapascal, PR or the reduced pressure has no value, reduced volume, which is here, PR is pressure ratio. Not pressure ratio, sorry, it is reduced pressure. It is ratio of P2 over P1. For isentropic process, it is somehow, related to the entropy also when, as I said, it is exponential of S naught at T over R, exponential of that for isentropic process. And R in kilojoule, the gas constant, and pressure in kilopascal. Now, if I want to change the units, we have the option here. One of it is the change units. If you look to the units, we selected temperature in centigrade and megapascal, and this will give us a specific volume in meter cube per kilogram, internal energy and enthalpy in kilojoule per kilogram, entropy in kilojoule per kilogram Kelvin. Actually, if I want in enthalpy in kilojoule per kilogram, I stick to this. If it doesn't matter the unit enthalpy because we are going to take ratio kilojoule per kilomole. I take this option, temperature in Kelvin and megapascal. If I have British, I can use this. Since we can have temperature in Kelvin, we can select this actually, but I selected the centigrade. You can do it the way you want, but in the solution I have in the lecture, I use this option, centigrade and megapascal. That's why temperature in the book, it is the example in your book, temperature was in Kelvin, I converted to centigrade, okay? Now, we need also to select the substance, it is air. You can select it from here, table substance. We specified it's air. Now, when I come to the calculator, I have a state 1, I have the pressure 0.095 megapascal, and the temperature was 22 centigrade, and calculate. What it does calculate, it gives me for temperature 22 and pressure 0.95 kilopascal, it gives me the specific entropy, a specific enthalpy. What I'm interested in is the enthalpy, and give the internal energy, specific entropy in kilojoule per kilomole. It gives everything, and it gives the reduced pressure, PR at 1. It gives PR at 1. Remember, this PR we are going to use to get P2. This PR at 1, what we have actually, let me open a new file. That all this I solved it before, insert equation. We have PR or P2. Let me write it properly to you. We have P2 over, for isentropic process with variable properties. This is what the equation we have it, P2 over P1 equal to what? Equal to PR2 over PR1. Equal to PR2 over PR1. Okay. Now, what he gave to us, he gave P2 over P1 equal to 6, right? Well, you are following with me? He gives this one equal to 6. So what we get from here, we can get from here that PR2 here equal to what? Equal to 6 times PR1, right? What is PR1? PR1 from thermodynamic table, he said 1.053, 1.05. So it is 6 times 1.053 equal to how much is this, Shabab? Can you calculate and let me know? This is 18, 6, 18, 6.
6.31.
6.31, right? Yes. Now, this is PR2. I'll take this PR2 and come here to the thermodynamic table. I want to state 2. State 2, what I have pressure 6 times this. What is 6 times this? 6 times this, how much? This 0.095 times 6, how much?
0.57.
0.57. What is the other property I should put here that reduce the pressure? How much? We said it is 6.31. So what we introduce the pressure 0.57, and this is at state 2, and this is reduced pressure at state 2, isn't it? Then what is the properties? What is important to me is the enthalpy, isn't it? This one. This enthalpy is important to me. Now at state 3, what we have at state 3, the pressure is 0.57 as it is, but the temperature, he said in centigrade, 1100 Kelvin or 827, right? 827 centigrade. He gave it. You see in the problem, the temperature is 827 at T3. As T3 here, he gave the temperature. So on thermodynamic tables, I put the pressure, which is 6 times P1, then I calculate. So state 3 given here, right? Now at state 4, What I need to know at state 4, similar like state 2, we can repeat all this. But I'll do it for state 3 over state 4. Let me put it 4 over 3. 3 over 4, make it 3 over 4, equal to PR3 over PR4. So I know the pressure at 4 is 0.095, right? But to get PR4, I need PR4 to get the enthalpy. So this ratio P3 over 4 is 6, equal to PR3 over PR4, right? So if I need PR4, how much? PR4 will be PR3. It will be PR3 over 6, isn't it? PR3 over 6. So it is now how much PR3 here? How much PR3 ya shabab?
134.
134.3. So we come here. It is 1. Let me make it in this 134.3 over 6. How much is this?
22.3.
22.3.
Yes.
Okay. Actually, it is 38,333, if I remember.
Yes. Yeah, correct.
Right. So we take this and we go thermodynamic tables calculator or this one, and we calculate state 4. What we have in state 4, the pressure is 0.095 megapascal. What is reduced pressure?
Victor, 0.095 and 0.57, this is already known, given to us, right?
Yeah, given from the data given.
Okay. Thank you.
And this is PR, we just calculate it, and then you say, okay, then we have state 4. Now, actually, to make my life nice, I can take up to the enthalpy, right? Because we need the enthalpy, right? It's what we need in our calculation for the efficiency. I can copy it and put it in Excel. I can have another sheet here, put it here. And I can make my table fine, nice. I can grab the text to make it, to save it. Format cell, alignment, wrap text. Then I have this centered. I made my life nice by using Excel. Just make it bold. Then what we have, the efficiency. Again, let me get from here the expression for eta. For variable specific heat now. Let us take for variable specific heat from my presentation. What is the efficiency? I can take this, isn't it? Work net over Q added. So I will take it here, just remind myself what I want to do. So I'll take efficiency here, copy. Equal to what? First bracket, H3 minus H4. Where is H3? This one. Minus H4. Where is this H4? Is this one. This is the work of the turbine minus work of the compressor, which is what? H2 minus H1. Close the bracket. Close the larger bracket, divided by Qin, which is H3 minus H2. Close the bracket. This is how much? 38%. So for constant specific heat, we calculated 40%. For variable specific heat, it is 38%. Right? Now, the difference here is what? 2% in the estimating the efficiency. But here, with a quick calculation in my calculator, and here I tried to use the thermodynamic tables, and I took time, or even I made a small ES code to give us the efficiency. You got the point? That this constant specific heat save a lot of time. But variable specific heat give you accurate, but it needs the time for calculations. So if you are in a meeting and you want to give a rough estimate to the committee, you can, while you are sitting, use your mobile calculator and get this 40%, right? Yes. Even when the computer, the Excel rounded, he rounds 38 to 40. Did you see that? It is rounding here by computer, by Excel. But the correct number is, so it's acceptable rounding. Again, I showed you here quickly how to use the simple formula, and this is simple Brighton cycle, simple Brighton cycle. But where is this 60%? Where it has gone, this 60%? Part of it were in the work of the compressor, right? Part of it in the heat loss. You see the enthalpy of the outlet gas, 700. But when I take fresh, I take air at 295. This 500 kilojoule per kilogram I'm losing. You see the difference here between enthalpy of the gas, air at inlet of the compressor and enthalpy of the gases we throw away. This 700, this is about 300. So 400 kilojoule per kilogram, we lose it. This is a big loss. This is a big loss. Even though it is more than the work of the compressor, isn't it? Now, what is the difference between what is work of compressor here? Are you following with me? Work compressor, I'm trying to see where is my loss. It's H2 minus H1, isn't it? This is the work in the compressor. 197 kilojoule per kilogram. This I'm paying, I don't take it, I'm paying it, which I subtracted here. What is the exhaust or Q cooling? That Q cooling is equal to H4 minus H1. How much it is? 400. Ooh, this is the real losses, isn't it? The exhaust. So this is the exhaust, is where I lose. What to do?
What is Q of C?
Q cooling. It is imaginary cooling. Didn't say that?
Ah, so it's the heat rejected.
The heat rejected. Yeah. This is the imaginary cooling. Because I lost at 7 and I take at 295. So what I lost is the difference. Because I give something to the air, to the surrounding, and I took something from it. So I gave and took, isn't it?
In that case, Doctor, how can we improve our efficiency?
This is to answer this, we go for this regenerative cycle. This is, I was preparing you to this. Actually, this is the calculation I summarized here in the PowerPoint. And I said to you how to use PR2 or for PR1. I summarized all the steps here. And this is even the Excel sheet, how I got it, with some little editing. And then I put for here the equation of the efficiency, because we focus on the enthalpy. I took part of the table I put here. So this is how we solve or improve or reduce the losses. We said that before I throw the exhaust gas here at the exit of the turbine to the surrounding. So why not, since I'm going to add heat by combustion here to these gases at 2 before the combustion chamber, why not to take some of this heat before we throw it away to the chimney, right? So we put a heat exchanger. This heat exchanger is called regenerative. The purpose of this is to keep some of this heat inside the cycle. So if I need to raise the temperature T3 here, since I heated part of the air, I heated the air from 2 to 5 here, right? Then to raise the temperature to 3, I will burn less fuel. I will burn less fuel. You understand? Because the heat, I added part from the exhaust gases and part from the fuel. But I want to sum up to give me the same enthalpy at 3. So this regenerative cycle, actually in the, most of the gas turbines I have seen, they don't install it. They don't install this regeneration because it complicates the plumbing of the cycle and the gas turbine, and usually it is compact, but they do have some other issue is to take this exhaust gas to boil water and use this water in a Rankine cycle that we are going to study soon. But this is the regenerative cycle schematic diagram that we take the air from surrounding at 1, we compress it at 2, take it to the heat exchanger here. Because why I don't mix it here with the air? Because we don't need to mix. Here exhaust gas doesn't have oxygen, fresh air has oxygen. So usually you don't mix them. We just make them interchange heat through a surface. They don't mix. There is a surface or wall between both, but this wall is good conductive for heat transfer. The shape of this regeneration actually differ from different companies, and it has different construction. You can read about it, but you heat the air up to point X and then go to the combustor, add less fuel to get the same temperature T3 and then expand here. So here what the heat you add now is from X to 3. So instead we were heating before from 2 to 3. So it was heat added was H3 minus H2. Now we have it H3 minus HX. X had temperature higher than 2. So you reduce the amount of heat you added or you burn less fuel. Then without regeneration, it was H3 minus H2. You see, you can see this on TS diagram. We were heating all the way from 2 to 3. Now we are heating from X to 3. And usually, since the heating gases is the hot gas at T4, which is always higher than T2, then the cold or the relatively air cannot, maximum when we heat it from 2 can reach what? Can reach T4, right? It cannot exceed T4, can it? Tx can be maximum equal to T4. Cannot go more than T4 because the hot gas is 4. And the hot gases will be cooled to Y, but Y this can always higher than T2, minimum it can go to 2, right?
Doctor,
now,
as the temperature at 4 will be the same at X?
Maximum X can go to 4. Because I have, let us say, hot gas and cold gas. Cold gas coming at 2, right? Remember, they have the same mass flow rate. Remember, they have the same, almost same mass flow rate, right? So the cold gas cannot be heated to a temperature higher than the heating gas, isn't it? I am heating, I have a source of temperature of heat at T4. So I will heat T2 will increase until maximum it can reach what? T4 maximum, but it will reach Tx, which is little less than T4. Actually, to make Tx equal to T4, you need a very big heat exchanger. You need a very big heat exchanger to give enough time for heat to transfer from this fluid to this fluid, from the hot to cold. But this will introduce a lot of pressure drop. Yes.
Dr. Ismail,
Thank you. The benefit of heat exchanger, from what I understood, is that to first to eliminate the losses to the surrounding.
To reduce your loss, because still we'll have a Ty, which is the exhaust now, minimum will equal to T. T2 is still high. T2, which is the exit of the compressor, is still high. To eliminate the losses, I should cool up to 1, isn't it? I should take this heat to the air up to 1, but I cannot go to 1 maximum because we are heating the air at 2. Remember, we cannot heat before the compressor. We are heating after the compressor.
Before, Doctor, we had, I've been exposed to combined cycles.
Yeah, we'll talk about combined cycles soon.
Yeah, just to not confuse with it, I'm confusing a little bit. Heat exchanger will only heat up the at the combustion, right?
Yeah, actually, it will heat the air. It is in the Brayton cycle. It is part. It will be part of the gas cycle, and it will try to keep the heat inside the Brayton cycle rather than throwing it away. It will try to keep it inside the cycle. We didn't talk about combined cycle yet.
Yeah, shukran, thank you.
So here, we cannot heat more than T4, okay? So since the heat exchanger has limited size, so the exit temperature for the air to be heated will be less than that of the gas coming to heat it. So this is called effectiveness of the heat exchanger or efficiency of the regenerator. Here is writing it efficiency of the regenerator, but efficiency of the heat exchanger is not a common terminology in heat transfer world, but they call it effectiveness, which is Hx minus H2. What is the heat gained by the cold fluid over the maximum possible heat gained by the cold fluid. The maximum possible is that the cold gas reached to T4, but it doesn't. It reached only to Tx. So this ratio of the actual heating of the cold gas, this is the actual heating over maximum possible. This is maximum possible, isn't it? This is the maximum increase in temperature, right? That cold gas come from 2 will be heated up to T4, right? But in reality, because the heat exchanger is not that infinite in surface area or not very long, we heat only up to Tx, which is little less than T4. So this ratio between the actual to maximum possible, we call it the effectiveness أو مدى فعالية الهيت exchanger or its efficiency. Here they call it eta regenerator. Okay. So this is another cartoon to define what is Q regenerated and actual Qn now. Instead of heating from 2 to 3, we are heating only from, let us say, 5 to 3. Instead of X here, we call 5. 5 prime is the maximum possible, right? But actual, we up to here. This is the when we have regeneration, then the efficiency for constant specific heat will be different from that for simple Brayton cycle. You remember the equation for simple Brayton cycle? It was 1 minus 1 over Rp to the power k minus 1 over k. This was down here. Now we have no T1 over T3, which is 1 over T, or this, the formula bit different due to some details. I don't want you to drive it, but I want you to know it. This is the efficiency of the Brayton cycle. If I take work turbine minus work compressor over Qn, which is now H3 minus H5, not H3 minus H2. This is simply the efficiency of the Brayton cycle. Okay. When we substitute with constant specific heat, this will be the formula. And the formula here will be like this: the efficiency at different T, value of T, the more the T3, the more the T3, you have the higher the efficiency. But the limit case is the simple. This is the simple Rankine cycle line. If we don't have the regeneration, if we have the regeneration, it will be this, and depend on how much is T3. T1 always the ambient temperature. T3 is the maximum after the combustion chamber. This is if we have a reversibility, so we have to take it into account for the compressor and for the turbine. And of course, TX here, usually the effectiveness or regeneration efficiency in the range of 60 to 80%. But again, 60% mean a small heat exchanger, or 80% if you have a larger surface area heat exchanger. The benefits of regeneration, we burn less fuel, as we said. This is the most important, and of course it increases the efficiency. Another way to improve the efficiency of the cycle, as I said, we add reheater. Like in the steam cycle, we have seen if you remember the efficiency of Carnot, or the maximum efficiency, 1 minus T low over T high. If we add heat at higher temperature, the average temperature of adding heat, or T high, we keep it always high, then the efficiency of the cycle improve. And this is the principle, is we add heat up to 3, then we expand in the very stage of the turbine, then we take the gases, or actually inject more fuel, more air, and the heat more here. Then we can heat, instead of continuing the expansion from A to 4 prime, no, we heat A to B, and then. So this area of extra work we got as extra work, but also we added here more heat. So always you compromise between how much work extra you take due to heat and how much heat you pay. But overall, the efficiency should to be improved. So as I said before, this is the science that when we have expansion at high temperature, we get more work, right? So because the lines are diverged here, he's not showing the diversion properly, but actually the work between P and 4 is higher than the work from A to 4 prime, because these lines of constant pressure, actually it is like this. So if I expand from here, 3 to A, then A to 4 prime, I get this amount here of work. But if I made reheat, as we said, reheat here, the line diverge, so I can get this more work here. You see here, this work compared to this. So when I add heat, I raise the temperature, I get more work from the same turbine, between the two pressure limits. That's why this is the science part that we learn from the properties that the pressure lines diverge from each other. So we decided to have the expansion in the high temperature region, and compression better we do it in the low pressure region. So can we have intercooling? I mean, instead, like we did have here, 2 turbine with interheating or reheat, can we make the compressor 2 stage and add intercooling? This is actually also is possible. But let us finish this reheat, how to calculate the efficiency. Efficiency is the area of the work, or work turbine stage 1 plus work turbine stage 2 minus work compressor over Q added, which is now I have 2 heat added from 2 to 3 and from here A to B, right? So this is cycle without reheat. This is the cycle with reheat. So here, if especially we have reheat, because we increase the exhaust temperature, we should have regeneration. If we have reheat, this means the exhaust gas will be at high temperature. So it's better to, if you have reheat cycle, you have to add regeneration to it. And this is if we like to have intercooling to make benefit of this phenomena or physical phenomena that the pressure line converge at too low pressure and diverge at high pressure mean expansion at high temperature give me more work, compression at low temperature give me less work or consume less work. And this is actually, if I made the compressor in 2 stages. So first stage, I cool from 1 to C, then I cool down in a cooler, I reject heat, then I compress from D to 2. So I reach to the same pressure on PV diagram, but you see this hatched area work I saved due to intercooling. We save work due to intercooling. Why? Because we make the compression in 2 stages and in between we cooled the air. In large compressors, they do this. Yani if you have a compression from 1 psi, from atmospheric, which is 14 psi, to about 3,000 psi, this has happened in SABIC for compressing, liquefying natural gas. You raise the pressure very high. Pressure, they don't make it in 1 stage, they make it in different stages, and they have intercooling to reduce the work in the compressor. But for a small compressor, we don't do this, right? So this is the real work I pay when I have intercooling before I have all this work plus the hatched area. So we save this. This is if I don't have, if I compress in 1 stage from 1 to 2 prime. But now, if I have intercooling, we compress first, let's say from 1 to C, then cool from C to D, then compress again from D to 2. So I save this area, I save this work. So usually the cycles, actually in TS diagram, if I cool, I compress 1 shot from 1 to 2 prime or in 2 stages. Actually, because the lines here, actually the shape of the line here, this drawing, they are not showing. It is not like this. It is, sorry, was this? It is like this. So first stage here, then you see here, you take this work plus this work. So compare this part with this part on TS or HS diagram. Of course, if you continue second stage here, continue from first stage without cooling, you will consume more work compared to if you cooled. Okay. So intercooling and reheat and regeneration. As I said, if you have reheat, you should have regeneration. But this happens if you have a high pressure ratio in between low pressure and high pressure in the cycle. So if you have high pressure, it's better to put intercooling as well. This is the complete cycle that, but as I said, the more you put heat exchangers in the cycle and reheat and regenerator, the more complicated is the plumbing and piping in the gas turbine. And usually it's not practical. Usually it's not practical. So what they do, Ya Shabab, I will, you want to take little break or we continue this and finish?
No, continue, Doctor, maybe.
Huh?
Continue for 15 minutes and then
15 minutes and close. Actually, the ideal cycle, if you have many intercooling, so you come close to isothermal compression, and also if you have many reheat, you come isothermal expansion. So we have two process isentropic or heat addition at constant pressure, two process heat addition and heat rejection at constant pressure, and you do have two isothermal. This is the ideal situation, but as I said, the more the reheat stages and more the region, the intercooling, the more complicated is the cycle. This is again a repetition of the reheat here, regeneration and intercooling cycle with irreversibility. You can, this work turbine, you have two turbines, so you have to take the total work of the two turbines. The compressors, you have two stages of the compressors. Also, you have to take the two stages. So on work net, the difference Then also you have two heat addition from 5 to 6 with the regeneration, and from 7 to 8 for the reheat. And the cycle calculation, the best here, instead of complicating your simple Brighton cycle, this is a simple one. Usually the turbine has exhaust to the chimney. So without complicating your gas turbine cycle, take the exhaust while it is exhaust pipe going to the chimney, make it heat liquid water that to boil, and you have now a steam at high pressure, high temperature. You can operate Rankine cycle. So we'll have what we call combined cycle, similar like simple Rankine cycle that taught to you by Dr. Hunter last module. And here the gas turbine here is similar to what we studied today. And now we exhaust, instead of 4 to the atmosphere, no, you take it to the, what they call it, heat recovery steam generator, which is a boiler, similar to the boiler, then exhaust to the chimney at 5, which is lower compared to 4. So you kept the heat, you make use of it, but not inside the Brighton cycle, but to run another cycle. So usually the gas turbine, they call it the top cycle, which is at high temperature, and the steam cycle, we call it the bottom cycle, because it is, of course, the highest temperature here is T4, it's close to T4, but here it is T3. This is what we call combined cycle. The combined cycle, of course, can take different shapes, and you can make a steam cycle with regenerative. Also, like explained by Dr. Hunter, you can make it very efficient, but the Brighton cycle, you keep it as simple, because the more complication, you lose the pressure drop, and it's very costly to make modification for gas turbine cycles. But the steam cycle, you can build it this way. And the work here, efficiency is work of the gas turbine part, the network, which is work turbine minus work compressor for the gas turbine. And here, network for the Weber cycle will be work turbine minus work pump. But we know that work pump is small, but over Q added, where we add heat only once in the gas turbine. Only once we add heat here. So the efficiency here will be very high. In the gas turbine cycle, we have seen the efficiency is around 40%. The steam cycle also is around 40%, but the combined cycle efficiency might reach 60%. Might reach 60%. Simple. If you know, steam cycle is simple. Rankine cycle is simple. Both we combine what through the heat exchanger by this. The heat lost by gases from 4 to 5 is gained by the vapor or liquid from 7 to 6. Both vapor, but actually state 6, it is saturated liquid, state 7 is superheated vapor. So both vapor, just to say it is a vapor cycle or Rankine steam, better to put steam here. So this is the link between the two cycles. The heat lost from 4 to 5 by gases is gained by the liquid or water in the other cycle. This Rankine cycle or combined cycle was sent to me this morning by Dr. Hunter. Actually, it is from LinkedIn. They have oil and gas website that I am, Hunter and I joining it, we get this. Let us quickly look at it. This is the gas turbine, the normal gas turbine. This is the compressor, as you can see here, followed by the combustion chamber around the shaft, on which there is the turbine. The turbine actually rotates the compressor and rotates the generator. As I told you in the beginning, the generator is always installed near the compressor, in the side of the compressor, because the turbine is at high temperature outlet. So the outlet of the turbine, instead of going directly to the turbine, we put this steam generator or heat recovery steam. It's called heat recovery because it recovers the heat from the exhaust. So we put the boiler part followed by the superheater, and then take the superheated steam to the steam turbine, and that rotate the electric generator, take work of the turbine, and the exhaust from the steam turbine, we take it to the condenser. The condenser can cool it by seawater or Gulf water if we are in the eastern province or on the Gulf or on the Red Sea. But if we are in an area like Riyadh, we can cool by groundwater. And this groundwater, we cool it by a cooling tower. We can cool the groundwater, and the groundwater will be here in a closed loop. And then the steam of the cycle doesn't mix with the cooling water of the condenser. This is in a loop. Then we take back the steam condensated, we take it back to the boiler or the steam heat recovery steam generator. Of course, we do have, since the water in the Rankine cycle is highly treated water, and due to some leakage, we might lose some heat, so we have water treatment for backup, and we can take steam for cogeneration. What is cogeneration? This is the schematic of the cycle shown here, a schematic for it here. This is the gas turbine cycle, and this is the steam cycle, and this is the link between this heat exchanger represents the boiler for the Rankine cycle and the heat exchanger for the gas turbine before the exhaust. Actually, we can put TS diagram. This is 1, 2, 3, 4 is the simple Rankine cycle on TS diagram with saturated liquid line, saturated vapor line. But this is actually without a scale, but this is the Brighton cycle on TS diagram. It is 5 to 6 through compressor, 7 to 8 through the turbine. Then 8 to 9 here is the heat. I take this. Take care that according to the drawing, we put the number of states that differ according to the drawing, so they don't get confused. That in one equation I wrote 4 to 5 for the gas turbine, but here I use 1, 2, 3, 4 to the steam cycle. So it doesn't matter, they are just number, but heat lost by the gases is gained by the steam or by water. In some other application, we have what we call cogeneration. So still here, this is a combined cycle, and still the steam coming from the turbine, I will cool it. Here we are cooling it by groundwater, and this might harm the groundwater if we reject heat at high temperature. So in some places you can take this heat for industrial process, like for example, clothes industry, they need hot water for painting the clothes. So they don't want to heat the clothes by direct fire. So they heat it by hot water, so we can take it to industry. Or in cold countries like in Europe, we have district heating. So they distribute hot water to the houses. It heat the house, then they return the water back to the condenser. So win-win situation. You want to cool the condenser and you want to heat the house. So you interchange heat here. This is called cogeneration. So this drawing here is a combined cycle, because you combine gas turbine with a steam turbine. This is the word combine. And cogeneration because you produce power from these two turbines. The gas turbine produce power, steam turbine produce power, but also you produce heat for industrial process or for houses. So this is called combined heat and power generation. So they call it sometimes CHP, combined heat and power in the same plant. From the same plant, you can take power, electricity like shown here, and also you can take heating for the houses, especially in cold places. This is example of the Cornell combined heat and power. According to the book, I don't know which year it is under construction, but again, you know the concept. You have gas turbine that help running the steam turbine. So both give power, and to the condenser where you reject heat to surrounding, instead of just rejecting to the surrounding, you use it to make both a small heat exchanger in houses connected together by a network. So you heat the houses and you take the return water to the cycle again. In some industry, you might again need this heat for industrial process. You take some steam from the turbine, and instead of having this regeneration, you take it to industrial process. So again, the balance here is simple. You see what you take heat and power here. So The performance of the plant, we don't call it efficiency, but we call it the utilization factor, because you add two values that is different in nature, both energy, but one in the form of work and one in the form of heat, but you added one heat here only in the boiler. This is also called cogeneration, but it is mainly a steam cycle. It doesn't have gas here. We cannot call it combined gas turbine and vapor. The title here is not suitable to this drawing. I'm sorry for that. No gas turbine here. I will correct this. Because this is mainly a steam cycle with the cogeneration. So we produce power and heat. Actually, we have here Azizia power plant and Jubail power plant. They produce power and water because they take the heat here in the condenser or from the bleeding steam here to make desalination. So here the industrial process in Azizia power plant or for desalination actually. So again, we have to take into account economic and energy, and this is what we'll do in next class. I will quickly say if we have in the gas turbine or in the steam cycle, we have boiler or we have combustion. Combustion usually have efficiency because in the boiler, you have fuel you burn, but you have exhaust that go to the chimney from the boiler. This is losses. And also sometimes you don't have complete combustion. Some of the fuel go out without burning. Then the efficiency of combustion is 90% usually. Then you have the cycle, either it is Brayton cycle or a steam cycle, efficiency is 37. Then you have the electric generator also is not 100% efficient. So the overall efficiency of the plant from fuel here, if we have fuel here, right, it has chemical energy and you have here electricity. So the ratio of electric power to the chemical energy in the fuel is multiplication of all these efficiencies. So it is 90 times 37 times 98 give you 33% of the whole plant, if you have a system that delivered to a system, each system has the efficiency of conversion. Here we converted in the boiler chemical energy into thermal energy. Then in the cycle from thermal energy to mechanical energy at the shaft. Then in the electric generator, we converted the energy from electric to, from mechanical, or shaft work to electric power. The ratio between the input and output here, our output to input, is a multiplication of efficiency of each conversion system shown in front of you. The economic, as I said, will start next class, inshallah. This for the gas turbine of the aircraft, similar to the one we have, but instead of here, you have the compressor, suck the air, combustion, then the gas turbine. But the gas turbine stages is made, is small enough to just to run the compressor. But the main power in the gases is introduced to a nozzle to give you thrust here, and the thrust time the distance over time, or thrust time the velocity of the aircraft give you the power used here, and this is the net power is the thrust time this velocity. Okay, I will stop here and I'll be happy to answer any question. Of course, we are not going to cover this much the aircraft part. You can read it. I'll leave it in the lecture. But you are welcome. I think we reached now to the. We should finish at 4, but we didn't take the break, so I'll stop here, unless you have any question.
Doctor.
Yes.
Yes, Doctor. The material is very rich, so if you don't mind to make a help session for us.
Yeah, I am planning to give a help session in solving some problems. I will arrange the times with Dr. Antar because you have a class test or something this week. Then yeah, I will arrange with him the class and also the problems we should cover. I prepared actually 5 or 6 problems from your book, but I saw the homework. I need to discuss valence and coverage with Dr. Amtar first
Can we
before
have
I
it-
discuss.
Can we have it next week, Doctor? Because this week, as you said, we need to study for the test.
Yeah,
And
yeah. This is what I want to tell you. I will not keep you busy with this because you need to focus on your exam.
Okay. Thank you so much, Dr. Smail.
Yes, yes.
Excuse me, Dr. Allah. I think this material is huge for 1 or 2 class. So I think if you are going to reduce it or to
First of all, this last
distribute
part,
it in for classes at least, because it's huge information and a lot of inputs and
actually, this part about the aircraft, you are not asked for it from here down. You are not from this one down. This part is the next module. I mean, this one slide will cover it in more modules. For solving problems on combined, we solve it simple cycle, right? But I want you to solve one for combined or for cogeneration. I mean, we can do it in help sessions. But according to the syllabus, I know the coverage, I just covered the material on module 1 because up to the syllabus, if you can look at it together, here the syllabus, yes. No, this is not the one. Yes. 1 minute, please, to share with you the syllabus according to what you have.
أنا دكتور بس our concept إن الماتيريال too much. إذا كانت الهلب سيشن ندرس فيها الأشياء المهمة للاختبار.
Yes, this is what I will do.
أي لأن الكونسبت أوكي يمكن توضح الحين من الشرح بس we need to know how to solve questions.
Yeah, let me tell you something. Actually, the first part we took from slide 1 to slide even about 74, right?
Yes.
And this was on the simple cycle. And we translated because there was general information, a lot of general information, just for your background. But the cycle analysis with constant specific heat or variable specific heat, we solve it in the example. And this part, if you understand the example, this is all what you need in the first part, which is about 80 slides. You need to solve one example like this, the simple cycle using constant specific heat or variable specific heat. So I might summarize this to give you one PDF file that have the most important topics or slides, most important slides.
Thank you.
Okay, but if you look at it, did you understand the example?
Yes.
When we solve it step by step.
100%,
but at least 60, 70%.
Yeah.
Yeah, fair enough. In a lecture, when you see first time and you understand 60 or 65%, this is fair enough, or this is expected, this is usual. Now you go read the example again, how we solve it, what are the important equations, that's it. You can forget about the general slides I gave at the beginning and focus on what is related to solving the problem, either a constant specific heat or variable specific. Variable specific heat, we get delta H. Constant specific heat, we convert delta H to CP delta T. That's it. Not more than this. I will clean from the general information slides to the specific information slides, and I'll give you short version of the lecture. Okay?
Okay, and next week then we can discuss it in the help session and have questions.
Yeah, of course.
Thank you.
Now, but let me tell you what we cover. We cover Brighton cycle. This is in your syllabus. We covered combined cycle. We covered cogeneration. Did I do more than this?
No.
Yeah, it is these 3 parts. Now, next time, economics, and then environmental impact. And instead of invited speaker, you will have your quiz or exam, I don't know. We can take these to solve more problems. if you don't have the exam on Saturday, you have it sometime else.
Yeah, it sounds good.
Right?
Yes. Yes. Great.
Thank you.
Great. Thank you, Doctor.
Okay, so you can leave if you want. Yeah, Dr. Hunter.
Yes, Dr. Ismail, here with you.
Now we are finishing.
Yes.
If you want to end the session or make recording the attendance or give us any comments if you want.
Oh, that's
he's explaining to something.
Yeah, somebody is
talking, feeling that he left. Maybe he didn't.
Sorry, I had to do. I had to. Dr. Ismail, can you just unmute yourself, please?
Oh, okay.
I had to mute all so that, that
because someone is talking on phone.
Yes.
He was talking on phone. Maybe he considered himself left, but he didn't.
Yeah, probably. Yeah.
Yes.
Actually, we just got an email. I think you have received it, Dr. Ismail, from Dr. Mohani. So we'll be talking about the exams in general. So essentially, it was some sort of expectation that we have the exam on next Saturday. But as I mentioned earlier, I'll just provide an update middle of the week or so that we would all know about the time, how it will be divided. It will be that duration of the exam expected to be like 90 minutes, and when exactly will it be and how it will be administered. So that's something that will be communicated by email, inshallah, in the middle of the week.
Okay, Doctor. But you have seen the comment of the student that the material is highly involved. Of course, it is involved if we want to talk all concepts into considerations. But part of the lecture actually was really focused on general issues rather than simplified version. But I can provide a simplified version for them to understand the main concept in Brayton cycle, combine and cogeneration.
Yeah, I think that will also be taken care of, as you mentioned, through an example, as it is solved and with them in the help session. I think that would clarify it all.
Yeah, but do you agree that I made a shortened version of the lecture focus on the calculation-oriented parts?
I think that would be a very good idea. If you remember that we used to use some sort of study guides that has been prepared by Schengel, I think that's just right to the point, and it just enables students to get into problem solving without.
I'll rebuild that.
That would be great.
You have seen the example I did with them through CAT.
Not really in details.
But it is in the lecture anyway. It is I summarized in the lecture already.
Yes.
I think this was. I mean, it took shorter time than I was planning or expecting.
Oh, I think if they went through it solved by hand, it will clarify a lot of the
points.
Yes, exactly. Yes.
Right. Anyway. Thank you very much, Dr. Hunter.
Thank you, Dr. Ismail.
I tried to cover all the 3 topics you put in the module 4.
Yes,
and we did. They need the, but I think your module 1 was more 1, 2, 3 also were very involved. I mean,
actually, we had to start because I know that many of the participants who are non-mechanical engineering did not take on thermodynamics. So we had to start from the very beginning because of that.
I missed the very first lecture because of the link. I didn't get.
Yes, that's right.
It wasn't Blackboard. You thought I saw it, but I was not having access to it. Anyway,
yes.
Yeah. But it seems that what I focus on, I mean, it is, I know all the courses involved. not only this part.
Yeah. I mentioned that once that actually this material we normally cover it in more than a semester, but try to cut out the fats and just put the things that will be needed for
exactly.
That would be needed for this kind of course.
The point here in this module, what is the difficulty for the students is that they will not study it directly because they want to focus on the exam. They will delay studying it until they finish their exam.
Yes, that's right. And as a matter of fact, we are always going to return this as our baseline. Like the Rankine cycle and the Brighton cycles are the ones who are making most of the currently for the power generation. And we need to have this as a reference, even when we talk about the renewable sources.
Yeah.
Either to come back again to Rankine cycle, or it has to come back again with some sort of a comparison.
But they have good technical questions, actually.
Yes.
Like
yes.
they really want to understand. They raise this question: what is the link between this and that? How to link it to sustainable?
Yes.
This was at the beginning. I think this idea will become clear and clear with time when we introduce the concentrated solar power and how we integrated that. Anyway, it seems that most of the students are still around.
Yes, maybe somebody has a question, then still we have Dr. Ismail.
So yeah, anybody has question?
No, Doctor, thank you so much. From my side, at least, I just wanted to say thank you. I mean, it was condensed, right? But yeah, I think you drove the point across from the components to the equations. I found it very useful. Thank you.
Right.
Now let my
Yeah, but if you can just quickly have a look at the lecture before you get absorbed in the exam, this will things fix things or sorts, but try to focus on the main parts as we said, till I summarize, inshallah.
Thank you, Doctor.
Thank you.
Thank you so much. Thank you, Doctor.
Doctor, one question.
Okay, go ahead.
What is isentropic?
Isentropic, sure. In English, they take any property to say it is constant. They add the word, the letters iso to the main word. Like entropy, we add to it isoentropy, so it will be isentropic, mean constant entropy. For the pressure, since we measure the pressure in bar, to say instead of saying constant pressure, they call isobaric. Yani the bar or the pressure is constant. For volume, they call it isochoric. For temperature, they call isothermal. When you see the word ISO, but when it comes it means the property is constant, like isentropic constant entropy. Constant entropy means no heat transfer, because you know delta S is definite by definition delta Q over T or del Q over T. So if you have delta S 0, mean constant entropy, no change in entropy, this means there is no heat transfer, and more than this, there is no internal friction that will generate internal heat to increase the entropy due to friction between molecules or so. So isentropic mean no heat transfer, no friction. This is the word, but as English, it is constant entropy. Physically, process with no heat transfer external or no heat generation due to friction internal. Okay.
Okay, thank you, Doctor.
You're welcome.
دكتور محمد.
تفضل.
السلام عليكم.
عليكم السلام ورحمة الله.
الله يسلمك. بخصوص الاختبار، حسب الجايد لاينز اللي شفناها من الجامعه انه اي اختبار 40 دقيقه واقل من الممكن انه يكون اونلاين، لانه يعتبر كويز. فما ادري هل ممكن انه الاختبار يكون في هذا الحدود بحيث اننا نتجنب موضوع انه لازم نحضر
لا هو مش هتحضر، هو كده انت مش مضطر تحضر. احنا حتى الاختبارات اللي عندنا الفصل الحالي، الكويزات او حتى الميد تيرم او الميجر اكزامز كلها هتكون اونلاين، وبالتالي انت you don't have to attend.
But I can add here, yeah, Dr.
اتفضل يا دكتور اسماعيل، اتفضل.
That based on the letter going around, that when you have a small class like ours, no need to have physical attendance. But when we have large number, like in the orientation on the prep year or something, they might have a physical attendance. But
بس حتى في الدنيا دكتور اسماعيل مش في كل الكورس.
مش في كل
الكورسات كمان.
Still the common courses.
Yes.
I mean that is coordinated and the grade is coordinated and this and that.
نعم. We don't have this kind of issue. So بالنسبة لنا
we don't have varieties between teachers. We are the same teacher teaching the same students. In the other classes, when you have 1,000 students or so taking the same course with different faculty, so we need fairness.
Yeah. So which means that for us, it will be anyway, it will be an online kind of activity, inshallah.
الدكتور ايش اللي حتبغى تتاكد منه من الدكتور محمد؟ ما وضحت لي.
هي في بوينت، يعني احنا في عندنا يعني في instructions احنا سبناها مثلا للطلاب. عندنا طلاب سواء السينيور او الجراديوت، ان احنا there is a certain way when we run the exam then you will be opening your cameras at a certain position. So sort of administrative things that I need to make sure first before I release it to you.
ممتاز. طيب دكتور، بالنسبه للاختبار انا اللي شايفه من السيلابس اللي قدامي حاليا تقريبا التركيز حيكون على رانكن فيبر سايكل ولا لا؟
نعم زي ما قلنا المره اللي فاتت I will be basically focusing on Rankine cycle. To be specific يعني I need you to look at the most general form of the Rankine cycle اللي يكون عندنا فيها reheat وفي generation كمان او regeneration. دكتور اسماعيل كمان اكد على الفكره بتاعت الريجنريشن ان الوركينج فلويد it needs to be further heated so that you can reduce the amount of fuel given in the heat addition part. So it's the concept.
يعني دكتور ممكن نقول انه الواجب اذا الواحد حله بفهم يكون يعتبر كافي؟
نعم.
طيب شكرا.
نعم ان شاء الله.
Doctor, do we expect any conceptual questions?
No. Actually, I'll just get into the hands-on so that you'd be able to solve the problem. If the concepts are clear, you'll be able to solve the problem without any issues.
Clear. Thank you very much.
So if you have no further questions, I mean, you can